Carúndios.
Okay, so we are back on live again. Hello, good afternoon, everyone. Welcome to the first session of today's afternoon, of the last day of PYCHeM. Without further ado, let me pass on the word to Professor Carlos, that will be the chair of this session. So Professor Carlos, whenever you want, you can start. Thank you so much. Enjoy the Congress.
Hello, good afternoon. So my name is Carlos Afonso. I'm from the Faculty of Pharmacy, University of Lisbon. It's a pleasure to be the chair of these three oral communications by three young PhD students that will present certainly a good work. So the first oral communication will be presented by Joana Madureira, from the Center of Nuclear Science and Technology at the Instituto Superior Técnico in Lisbon. So Joana is, as I said, a PhD student. She will present the work on optimization of heat-assisted extraction of bioactive compounds from olive wastes. So please, Joana, take your time.
Thank you, Professor Carlos. Just share my screen. Are you seeing? Are you seeing my screen?
Yeah, just a moment.
Are you seeing now?
No. Okay, no.
Yeah, it's fine. It's fine, Joana. Go ahead.
Yes, it's fine.
Yeah.
Okay, thank you for the presentation, Professor Carlos, and thank you for the organizing committee for the opportunity to present some results of my PhD work. Olive oil production is an important industry in the countries of the region of the Mediterranean. They produce more or less 95% of the olive oil in the world. And during the olive oil extraction, there are a lot of waste generated, and a wet pomace, that is a combination of olive husk and olive meal wastewater. And this pomace has a lot of organic compounds, sugars, tannins, lipids, and other lignin substances, and also phenolic compounds. These compounds are considered pollutant if they are discharged into the environment, but they are known also by their potential use as food bioactives, since these natural ingredients can bring additional value to the final food products. So, I don't know if it's, sorry. Yes, okay. In one of the host institutions where I'm doing my PhD, in Centro de Ciências e Tecnologias Nucleares, we have two facilities of ionizing radiation, a cobalt-60 source, and an electron beam accelerator. And our previous works demonstrated that both gamma and electron beam radiation can induce different modifications on antioxidant properties. And we have studied a lot of different matrices, aromatic plants, also in collaboration with the group of Instituto Politécnico de Bragança, wastewaters. This example is wastewater from cork industry, but also different fruits like strawberries, raspberries, cherry tomatoes. And what I wanted to do in my PhD was to use this ionizing radiation in olive pomace to see the impact of the radiation on olive pomace. And I started to see what happened to the extractability and to the antioxidant properties of these wastes. And in this paper that I published last year, I used 4 different doses of radiation from 5 to 22 kilograms, not only to see the impact of radiation in these wastes, but also to choose the best absorbed dose to use if the results are promising. And as I expected in this work, I observed that the most abundant compound in olive pomace was hydroxytyrosol, and followed by other derivatives, hydroxytyrosol glucoside, tyrosol, and others. And I observed also that no hepatotoxicity in non-tumor cells was observed, because I studied the impact also in the bioactive properties of these wastes. And I observed that these wastes had a potential antibacterial activity. Concerning the effect of gamma radiation, I observed that in the studied wastes, there was an increase in the extractability of phenolic compounds from it, more than 2-fold, what is very good, is a very good result, and also an increase in the antioxidant activity of the olive pomace irradiated at 5 kilograms. Also, I observed no effect on hepatotoxicity and antibacterial activity. So I concluded that gamma radiation at 5 kilograms can be a suitable technology to valorize the olive byproducts, not only because it contributes to enhance the extraction of phenolic compounds, but also enhance the bioactive properties. So next step was to optimize the extraction of phenolic compounds from these irradiated olive pomace, irradiated at 5 kilograms. And for this, I utilize first of all the heat-assisted extraction. To this, to optimize the heat-assisted extraction, I used the response surface methodology with the 3 variables: temperature, solvent, and time. Temperature ranged from 25 to 85 degrees, solvents from 0 to 100% of ethanol, time from 20 to 120 minutes. And I used a solid liquid ratio of 30 grams per liter. My responses, my studied responses were 11. Extraction yield, and the other 10 were divided by the individual compounds, the major compounds of my samples, and I added caffeic acid just as a, how can I say, a representation of phenolic acids present in the olive pomace. And the other responses was total phenolic compounds. And these I made by HPLC quantification. Just to show some results, I used a design of 28 runs, and extraction yield ranged from 2.8 to 19.3%. And the higher values, the higher yield was obtained at run 26 with 70 minutes, 55 degrees, and 50% of ethanol. Then just talking about the single factor effects, looking at extraction time, we can see a small but positive trend, implying that the extraction of compounds was higher for longer times. Looking at temperature, we also observed a positive trend, and the extraction of it seems that the extraction of compounds is higher for the maximum tested temperatures. Concerning the solvent concentration, we observed different significant statistical differences for all the responses and a strong variability among them. I want to also show that the experimental data were fitted to the second-order polynomial model. And as we can see here, the coefficients of determination are higher than 0.94, which means that the model fits with high correlation and precision. Concerning the optimization of heat-assisted extraction process, we can see that the global factor values that are here for maximizing the responses that we want, so individual compounds for the maximizing of the individual compounds amount, and also the total phenolic compounds. The optimal conditions were achieved at 120 minutes of time, 85 degrees of temperature, and 76% of ethanol. In these conditions, we obtained 19 milligrams per gram of dry weight and 148 milligrams of extract. And the recovery yield was 13.7%. As I said in the beginning, hydroxytyrosol was the main, the most abundant compound in my samples, and here we can see that we achieved a good recovery amount. And comparing our results with others using pressurized liquid extraction, we can say that our values are higher. So as conclusions, I can say that olive pomace is an important source of bioactive compounds. Gamma radiation, as I told you, enhanced the extraction of phenolic compounds, being a suitable technology to valorize the olive oil byproducts. Concerning the heat-assisted extraction, I observed that the higher extraction can be achieved for longer times and at high temperatures, and the optimal conditions were achieved at 120 minutes, 85 degrees, and 76% of ethanol. The recovery amount was almost 150 milligrams per gram of extract. Now I'm optimizing the recovery of phenolic compounds of hydroxytyrosol and tyrosol by ultrasound assisted extraction. I want to compare the results, not only the extractability of the compounds, but also the bioactive activities of these extracts. I want to compare the ultrasound-assisted extraction with the heat-assisted extraction that I mentioned here. In the end, I want to incorporate these extracts as preservative ingredients in bakery products. I want to thank the FCT and the other programs the International Atomic Energy Agency, and also to my supervisors from different institutions, from Instituto Superior Técnico, Instituto Politécnico de Bragança, and Universidade de Salamanca. I want to thank you for your attention, and
okay.
thank you.
Thank you very much, Joanna, for this presentation. At the moment, we don't have questions, but certainly I have. And my first curiosity is, what was the scale of your experiment, and how, if you can describe the apparatus you use for these experiments?
Sorry, can you repeat, please?
What was the scale of these extraction experiments?
The scale?
Yeah,
the laboratory scale?
Yeah.
Yes, just in laboratory scale for now.
But what was the volume of the reactor, and how is the reactor? If you can explain a little bit better.
I don't have any photo, but it's the volume. It's 20 milliliters. It's 600 milligrams of solid of olive pomace for 20 milliliters.
Okay.
Yeah, it's just.
Okay, thank you very much. I think we're just on time, so I need to move on to the next presentation. So if you can, so the next presentation will be given by Paula Oliveira from Universidade de Vigo, and she will present her work on in vitro bioactive potential of several microalgae species.
Can you see the presentation?
Yeah, it's fine, Paula. Go ahead.
Okay. Thank you very much for your kind presentation. I'm Paula, a predoctoral student from the University of Vigo, and I'm going to present the results of a research study that I've made at the Polytechnic Institute of Braganza. Until a few years ago, the consumption of macroalgae was a typical food habit of the Asian countries. But nowadays, the consumption is spreading in the Western countries due to a higher demand of the consumers for food with good nutritional values and health benefits. All this is quite a significant challenge for the industry, for the food industry, which is constantly searching for new ingredients. Nowadays, several products could be found in the market that contain macroalgae, such as salads, soups, or snacks. Specifically, these organisms are rich in non-digestible polysaccharides, proteins, vitamins, and minerals, while they have a low lipidic content. In addition, numerous studies have reported the presence of different bioactive compounds that may have beneficial effects on the health of the consumers. However, the composition of these organisms varies according to several factors, such as species, season, the climatic conditions, and also the process of manufacture the food product. Some of the biological properties that have been attributed to macroalgae include antioxidant, anti-cancer, neuroprotective, antimicrobial, and these properties are usually linked to the presence of different bioactive compounds such as polysaturated fatty acids, pigments, sulfated polysaccharides, and organic acids, phenolic compounds, and proteins. So the main aim of this study was to determine the biological properties, namely antioxidant, antibacterial, and antifungic activities of 6 species of macroalgae that could be found in the Galician shores. We we have 4 brown macroalgae, Immantalia elongata, Laminaria acroleuca, Saccharina latissima, and Undaria pygnophytida, and we have 2 red species, Porphyra and Palmaria palmata. First, the samples were collected from the Galician shores, and then they were washed to eliminate sands, impurities, salinity, and they were dried and grinded to obtain an homogeneous powder. Then this matrix was used for the extraction, which was carried out by maceration, and then the extract was evaporated and lyophilized to obtain the dry extract that was subsequently dissolved in water for the following to perform the following assays. The first one, we carried out the auxiliary assay to evaluate the antioxidant activity of the extract using sheep blood erythrocytes. This assay is based on the evaluating the ability of an extract to inhibit the membrane damage caused by the free radicals, the AAPH. And then we have the antimicrobial assays. We test these extracts against 3 gram-negative strains and 3 positive bacterial strains and 6 species of fungi. In this assay, we determine the minimal inhibitory, the minimal bactericidal, and the minimal fungicidal concentration. Then we have the results of the antioxidant assay, the auxilia. As we can see, the half minimal effective concentration varied between 1.7 and 650 micrograms per milliliter of extract. Specifically, Immantalia elongata, Laminaria acroleuca showed the best results, the best antioxidant results, even better than the than the Trolox, that was the control. For the case of Saccharina latissima and Undaria pygnophytida, no antioxidant effects were observed, which indicates that these extracts did not have the ability to protect the cells from the hemolysis. Then we have the antibacterial activity. All the tested extracts showed the ability to inhibit the growth and also showed a bactericidal potential against several of the bacterial tests. But the results were not similar of those reported from the control, the streptomycin. In this case, Immantalia elongata showed the best potential, and Micrococcus flavus, Salmonella typhimurium, and Enterobacter cloacae were the most susceptible strains to the different extracts. And finally, regarding the antifungal activity, similar results were observed. All the extracts were able to inhibit and also exerted fungicidal activity, but they were not comparable to those observed in the case of the control, ketoconazole. Laminaria acroleuca and Saccharina latissima were the most effective extracts, and Aspergillus niger was the most susceptible fungi to the extracts. So, considering these results, brown algae present a stronger in vitro activity. In the case of the antioxidant assay, Laminaria acroleuca and Immantalia elongata showed the best results. In the antibacterial assay, it could be highlighted the effectivity of Immantalia elongata. And finally, in the antifungic assay, Laminaria acroleuca and Saccharina latissima showed the highest antifungic potential. Thus, concluding, this study shows that this species could be used in the nutraceutical industry as new food ingredients to develop new foods with diverse biological properties and high added value. So thank you very much for your kind attention, and thank you to the committee for giving me the opportunity to present these results. Thank you very much.
Okay, thank you very much, Paolo, for your presentation, also for taking exactly the time required for this. Um, I wait to see if some questions appears. If not, um, my my first curiosity is what are the plans for the future work during your PhD?
We will try to extract specific compounds for the antioxidant activity and the antimicrobial to characterize which are their mechanisms, and maybe we will try to optimize their extraction
Okay,
in the future.
okay. And Paula, can you give us an idea about the comparison between the algae that you studied and with other algae from other types? If there is any study with a similar um, evaluation.
Sorry, can you repeat?
Can you compare the results with any other
In
results for other algae?
yes, in the case of Auxilia, none other studies have used this assay. But in the case of the antimicrobial and antifungal assays, we have found similar results in the bibliography, but not for all the samples, all the algae test.
Okay, and just yeah, there is no other questions. So I just would like to know. I didn't. Was not possible to hear the beginning of your presentation, so maybe you gave those details. But can you give us an idea the amount of compounds that are present in this algae?
The amount of compounds.
Oh, compounds, yeah.
We have made first we made an initial characterization and with a nutritional characterization about the proteins, the carbohydrates, the proteins and ashes, and we also found we also carry out a chemical characterization about the pigments and the oxalic acids and fatty acids. In general, more or less, they have the same the composition. The red algae have more amount of proteins, while the brown ones have usually they have less. But we have compared these in the bibliography, and we found that the content is really variable, and sometimes, especially with Undaria pinafitida, we have very variable results. And then we found that they are a really good source of fatty acids. I have not with me the results, but I think they are a good source of linoleic acid, and they also have some organic acids, mainly oxalic acid.
Okay, thank you very much for your presentation. So we'll move to the next presentation that will be given by Anxo Carreiras Casais, also from the University of Vigo, and he will present the work on ultrasound-assisted extraction of fuchsoxanthin in Ascophyllum nodosumu alga. Probably I didn't say the name correctly, but certainly Axel will spell this perfectly. Please.
Okay, thank you very much for the kind presentation. I'm going to share my screen and I'm going to start the presentation. First of all, I want to thank the organizing committee for the great opportunity to be here to tell to you my work about ultrasound-assisted extraction of fucoxanthin in Ascophyllum nodosum. That was a work that take place in University of Vigo, but it have the collaboration of Instituto Politécnico de Bragança and also Center for Research and Development in Food Biotechnology of CONICET Argentina. So I'm going to start talking about macroalgae. Macroalgae are a novel source of compounds for food industry in Europe. This kind of food is typical from Asian countries. So Japan is a traditional consumer of this kind of food, but in Europe is not also as traditional as in Asia is. And macroalgae are really useful to foods, and they are a good source of ingredients for development of nutraceutical new ingredients and new foods, because macroalgae are rich in non-digestible polysaccharides, proteins, vitamins, and also minerals. Macroalgae are also low in lipidic content, and they have a lot of biocompounds with health benefits. Among these biocompounds, there are fucoxanthin and also pigments like chlorophyll that can have some bioactive activities. It is in a study also the polyphenol composition of the macroalgae that could be also a source of bioactive compounds. Well, the seaweed that we chose for doing this study was Ascophyllum nodosum. Ascophyllum nodosum is an edible algae that is typical from Galician coast. This algae habits North Atlantic coast between Ireland and to Portugal. It's characterized by its content of protein, lipid, and an important content in ash. And due to this high content in protein, is useful for the extraction of amino acids. Also, Ascophyllum nodosum is rich in pigments such as chlorophyll, but it's also rich in fucoxanthin. That is the pigment in which we are interested in this work. The importance of fucoxanthin is his associated chemoprotective properties and also his associated antioxidant properties that are being studied in a lot of studies in recent years. The benefits in metabolism of lipids and consequently the weight disorders are also in study. So our study consists in the extraction using ultrasound-assisted extraction. We can say that ultrasound-assisted extraction is a novel method of extraction that belongs to the group of green chemistry because it allows us to perform extractions with lower amounts of energy and also employing less amounts of organic solvents. First of all, we take the raw material, the raw Ascophyllum nodosum that arrive to us from industry, and then we perform a lyophilization of the material. Then, when the algae is lyophilized, we perform the ultrasound-assisted extraction, employed the different conditions that we have optimized using a response surface methodology. In this response surface methodology, we optimize the temperature, the time of extraction, the powers of extraction, and the conditions of the solvent, the percentage of ethanol and water. That is the solvent that we employ. Then we achieved these extracts, and with these extracts we perform the determination of fucoxanthin, the amount of fucoxanthin in the sample, and the dry weight, that is it's present in the sample. And well, Then we perform the response surface methodology using 5 levels of 3 independent variables that I said before. One of these is the time, then is the ethanol, the concentration of the solvent, and also the power employed in the ultrasound-assisted extraction. That is between 100 watts and 500 watts. And we can conclude that the optimal values of the evaluated conditions were high proportions of ethanol, lower time and power, and medium solid ratio, obtaining 90.5 milligrams of extract per dry weight of sample of alga and 550 micrograms of fucoxanthin per gram of dried weight sample of alga, and 6.5 milligrams of fucoxanthins per gram of extracts. That we can conclude that ultrasound-assisted extraction is an ecological, fast, and simple technology that allows us to obtain large amounts of fucoxanthin with lower energetic consumptions employing this type of algae, this Ascophyllum nodosum, and we are able to employ this methodology to obtain fucoxanthin in other type of algae. So I want to thank you to the attention, and that's all. Thank you very much.
Okay, so thank you very much for this presentation. We don't have questions from the audience, and I was interested some time ago on this molecule that you mentioned, the fucoxanthin. What is the color of this dye? It's not only a dye, but certainly has some color.
The color of fucoxanthin is orange.
It's orange. Is it stable?
I think is thermostable. It's not thermolabile, but with the time is not very stable, I think.
With the time, with time in the air, or just or under nitrogen?
It's better to preserve the fucoxanthin in the fridge, in the -80, because if you let the sample in the lab, the fucoxanthin disappears, I think, degrades.
Oh, degrades, okay. Yeah. And as I asked before, the amount of fucoxanthin in this algae is higher than in other ones, because this has been studied quite a lot, the amount of this fucoxanthin in different natural sources. So can you comment on that?
I think the amount of fucoxanthin is higher in Undaria pinnatifida wakame, but we are looking for fucoxanthin in all the brown algae. We're using some algae, and we are trying to extract this compound in some algae, because in Galicia we have edible algae typical from Galicia, and also invasive algae. So in this time, Ascophyllum nodosum is an edible algae, but sometimes we try this extraction using non-edible algae, because we want to revalorize it or achieve an use to a non-edible algae, for example.
Okay, so use ultrasound-assisted extraction. Can you comment to us what are the advantages of this extraction regarding to traditional ones, and if you can compare the efficiency of your method to the other methods?
We are going to compare the efficiency of ultrasound-assisted extraction against sourceless extraction, because sourceless extraction is one of gold standard extraction methods to extract lipidic compounds.
Okay, and yours seems better, or you don't know?
I think I'm not sure about the effectivity compared with sourceless, but ultrasound-assisted extraction have some advantages. One of these is the lower consumption of organic solvents, because when you perform ultrasound-assisted extraction, you only have to put, for example, 50 milliliters of ethanol or water ethanol. But in the case of solid extraction, you are performing an extraction with at least 100 milliliters of ethanol or something, or other organic solvent. And then when you perform an extraction employing ultrasound-assisted extraction, you have a extraction in 5-10 minutes. It's okay. But if you perform the extraction using Soslet, the time of extraction is longer.
Okay, and there is still no questions. We still have some time, so I will take the opportunity to clarify a little bit better this system, because I think, at least for me, is important to learn. Can you comment about the scale up possibility of the ultrasound extraction in comparison with other methods? Is it possible? Do you have an idea about to scale the process? If you think about for industrial application of ultrasound, do you have some comments?
I think it's able to apply ultrasound-assisted extraction from industry application, because you can obtain a bigger one ultrasound to perform this methodology at a great scale. I think it's able to employ a great scale in industry. I think in this way it's fantastic. The only disadvantages of the ultrasound-assisted extraction, in my opinion, in this case, is that ultrasound-assisted extraction produce great amount of temperature when you perform a large extraction with high power. So you have to design a correct reactor with a correct refrigeration to perform to control the temperature. But in the case of Fukushima, it's not a problem, because Fukushima is not thermolable in my mind, I think. So so I think is able to perform the extraction of Fukushima. Is okay, this method.
Okay, just a final comment. Can you tell us what are your plans for the last part of your PhD on this topic?
Well, our plans are doing performing the extraction of Fukushima, and also trying to search some application for nutraceuticals also of this compound, for example.
Okay. Thank you very much for your presentations, also for the also answers that you did.
Thank you very much.
Okay, before we finish this section, after Joanna's presentation, my colleague Professor Ana Ricardo from Faculty of Science of Technology at Nova, she gave a question, so I will request Joanna to use the few minutes to answer that. So my colleague said, you improve the yield by increasing temperature. And the question is, did you also evaluate the selectivity of the extraction process? So Joanna, if you could give some comments on that.
Yes, I don't know if I have understood well the question, but to select the independent variables, we made some preliminary tests to choose the time, the levels of time, temperature, and the solvent concentrate, solvent percentage. And yes, with the higher temperatures, we achieved higher recover yield.
Yes, Joanna, but I think the question of my colleague probably is different. The question is more if you found some difference on the proportion of the different components, such as hydroxytyrosol and the others, depending of the temperature. I think this was the question.
Yes, yes, I found, yes.
But which one appears in higher amount at higher temperature and at lower?
Hydroxytyrosol was always the most extractable compound, and the others I'm not sure. I have to check, but if Professor wants, we can send emails or something. But yeah, hydroxytyrosol is always the most abundant compounds that are extracted. Yes, yes.
Yeah. Okay, Joanna, thank you very much.
You're
and
welcome.
Thank for all the presenters of this afternoon. So we'll close now this section. And
thank you so much, Professor Carlos, for your work in this session. Thank you so much for the pertinent questions, and also thanks to the oral communicators. They did a great job. Thank you for sharing your work with us. So let's move on to the second session of today's work that will be chaired by Professor Paulo Branco and Professor Emilia Souza that will present the first National Retrosynthesis Competition 2020 Awards. So I will pass on the word to you. Thank you and see you soon.
Hello. Boa tarde a todos. Nós vamos hoje apresentar a Competição Nacional de Retrossíntese. É um evento nacional dirigido a jovens químicos, numa organização conjunta das divisões de Química Terapêutica e Química Orgânica da Sociedade Portuguesa de Química, e este prémio visa promover o conhecimento e raciocínio nestas áreas desenvolvido por jovens investigadores e é atribuído com o patrocínio da empresa farmacêutica Bial, representada aqui nesta sessão pelo Dr. Paulo Vital, químico terapêutico sénior do Departamento de Investigação, a quem agradecemos a presença. A competição tem por base, numa primeira fase, o desenvolvimento de um plano de retrossíntese, de uma molécula colocada a concurso, e numa segunda fase, a respectiva síntese. Ora, foram apresentadas 9 candidaturas de equipas com afiliação de norte a sul do país, o que demonstrou o dinamismo que o concurso disputou nos jovens químicos portugueses. Destas 9 candidaturas foram selecionadas 4, que passaram à fase seguinte de desenvolvimento de um plano de síntese. O júri participa também nesta sessão, sendo constituído pelos professores Augusto Tomé, da Universidade de Aveiro, a professora Matilde Marques, do Instituto Superior Técnico, a professora Teresa Pinhamel, da Faculdade de Ciências e Tecnologia da Universidade de Coimbra, a professora Maria Amparo Faustino, da Universidade de Aveiro, e é presidido pelo professor Artur Silva, presidente da SPQ. Agradeço a todos e cumprimento, e apresento também os meus cumprimentos. Ora, eu passo agora a palavra à minha colega, a Emilia Souza, da Divisão de Química Terapêutica, também para dizer umas palavras e, portanto, passarmos à apresentação dos candidatos.
Exatamente, eu irei pedir aos finalistas agora, vamos passar a essa apresentação dos planos de retrossíntese e síntese da molécula-alvo desta primeira competição, que se encontra aqui atrás de nós. A apresentação chama a atenção, não pode exceder os 12 minutos e no final o júri e os elementos do júri terão a oportunidade de questionar, levantar algumas questões que possam surgir das vossas apresentações. E eu pediria então à primeira equipa, PYCHeM CCMAR, da Universidade do Algarve, cujo elemento é Patrícia Amado, que eu já vi que estaria aí, para compartilhar a tela. Muito obrigada e dar início então à sua apresentação. Patrícia.
Boa tarde. Um momentinho, conseguem ver?
Conseguimos?
Sim, ok. Deixa eu começar. Okay, boa tarde. Good afternoon. My name is Patrícia Amado and I'm a PhD student from the University of Algarve. And today I'm going to present my proposal for the National Heterosynthesis competition. The target molecule is Shinrin, as you can see here, and just a small introduction about Shinrin. Is a mycosporin-like amino acid, and Shinrin has been used as a key active ingredient for environmental-friendly sunscreen cream and is produced from a natural source, the red algae Porphyria umbilicalis. So from where do we start in the retrosynthesis of Shinrin? This is the retrosynthesis plan, which involves basically 2 routes. And the starting material is skinic acid for the both of the routes, which they diverge, eventually converging for the second, for the compound one, which is the glycine mycosporin derivative, which is the precursor of Shinrin. The first route is also called the most reported in the literature because White's research group, they published a paper of the synthesis of compound 1 from quinic acid with the 11 steps of reactions. And then the second route will be like an alternative route with the shorter steps and to go to improve yields and reduce cost and also save time. And as you can see here, the synthesis is quite flexible, and we will see that there are many ways to alternate in case of some problems during the synthesis. Starting with the first synthesis, which is common from the both routes, involves acid-catalyzed acetylization of quinic acid with benzaldehydes, followed by a gamma lactonization, as you can see here, affording this quinine in very high yields. For the first approach is when the quinine is when the reaction, the routes start to diverge, as you can see here. For the first approach, as supported by White's research group, they treated this quinine with NBS followed by a bromination and gave the corresponding bromobenzoate in quite good yields. For the second step, I suggested to do a mild reduction with sodium borohydrate, which will reduce the lactone and giving the corresponding triol, as you can see here. And the next step will be doing protection of the vicinal diol by a catalyzation with acid-catalyzed reaction. Both of these reactions are already been published in the PYCHeM report and has quite good yields. For the third step of the first proposal of White's research group, they did similar reactions. They also reduced the lactone followed by a catalyzation of the vicinal diol. In this situation, they got two isomers because they are in the previous reaction, they opened the acetyl ring, and this gave two different isomers. One of them was unexpected, was isomer A, which was a partial migration of the benzoate ester to the peripheral oxygen. This is called like a serendipitous reagent because they were not expecting of obtaining this isomer A, but they used for the next reaction by oxidizing with PCC the single alcohol function to the corresponding ketone. The same procedure I adapted for the second step of the second approach, which involved oxidation of the single alcohol group function to the corresponding ketone as well. Continuing the synthesis, White's group, they did net displacement of bromine with benzene sulfonate to add the corresponding sulfonyl moiety, changing with the bromide with retention configuration. This happened because of the continually tautomerization of these compounds, and the enol form can be reacted with the diazomethane, promoting methylation of the hydroxyl group, as you can see here in quantitative yields. And then the authors, they perform the protection of the benzyl group, achieving the single alcohol. For the second proposal, I decided to adjust the protocol from White's and also treat the intermediate with NBS to promote the acetyl ring opening and giving the exclusive bromobenzoate as backup from the PYCHeM report. This compound can then be reacted with sodium methoxide by a nucleophilic substitution called SM2, and we change the bromine with the methoxide group, as you can see here. They are backup from different papers from the literature. The only drawbacks of this reaction is due to the strong basic effects of the sodium methoxide, which could affect slightly the benzyl group, which can remove and affect the yield. And also we are dealing here with a secondary carbon, so it's possible that we may generate some byproducts from the elimination reaction as well. Following, the next step of the second approach will be doing a dehydrogenation to give the corresponding alpha-beta unsaturated ketone. There are different papers that could back up this reaction, which are compatible with both protecting groups and also for the function group as well. The work from Harris and also the work from Kals et al. With iodine catalyzed, a paper from last year. Continuing with the second approach, we're almost in the end of the second approach. We'll be removing both of the protecting group by acid catalyzed for the ketol protecting group and reduction to remove the benzyl group. and affording the corresponding dioxygadazole. The 4-dioxygadazole has been used as a starting material for many enzyme-catalyzed biosynthesis. And one of the Young's reports, they use a modified algae Synecocystis as a heterologal host to add both of the amino acids. First, they start adding the glycine amino acid, affording the compound 1, followed by addition of serine with a different enzyme to get our target compound with the Shinrin. So we finish here the second proposal. For the first proposal, White's group still have some things to do because we don't have the compound 1. They perform oxidation of the hydroxyl group, followed by a substitution with the sodium azide. The goal here was to be able to introduce amino function group, and how they did that through a reaction of the azide form with triphenylphosphine to achieve the corresponding aminophosphorin, called the Staudinger reaction. This type of reaction is this type of compound of aminophosphorin are very common to be used in the so-called azoitic reaction, which they react with aldehydes, ketones, so on. And this was the case. It reacts with a benzyl glycosylate, achieving the corresponding imino, followed by a reductive amination to give the corresponding amine. As you can see here, this is basically the glycine protected with the benzyl group. So to achieve compound 1, we just need to remove both protecting group by catalyze for the ketone protection, and then hydrogenation to remove the benzyl group. And we get our precursor of Shinrin that can be synthesized by enzyme catalyzed synthesis, as the previous report I showed you from Young's, or we could go to a more traditional chemical way by synthesizing in methanol and water and corresponding amino acids, synthesize the chief base. There are protocols that could back up from the work from Martinez, for example. There's only drawback in this synthesis is because it may form both isomers, E and Z, and we may need to do some chiral separation to obtain the pure isomer. So this is the summary of both synthetic routes. In blue highlighted is the first approach, which involved 12 steps, as I said. All of the steps are described in literature, except for the last one, which is only enzyme catalyzed. We will see if the traditional chemical way is possible to achieve. In case for the second approach is highlighted in red. The goal here is to improve yields from the first approach and reduce cost and time. Although there are a few reactions that we need to still check if it's possible because they are not described in literature. In terms of if we need to do some adjustments, for example, in terms of adjustments, as you see, there are many ways to approach, especially for the first approach. And also we can also think of alternatives to improve the second approach as well if it's needed. So for the final remarks and conclusion, 2 different approaches have been proposed for the synthesis of microsporin-like derivative Shinrin from quinic acid. The first proposal was the most reported synthesis in the literature, as I said before, hence with a higher probability of success. Different studies were suggested to circumvent any possible incompatibility in the first plan. And the proposed novel approach offers a synthesis with fewer steps than the first approach, although 10 versus 12, although it's not completely described in this literature, opposite from of the first approach, except for the last step, as I showed you before, which could be a problem. So there will be a risk of failure or not. We need to see it. So in the end, what matters is the yield and cost, and will be taken in consideration to decide which pathway is the best for the synthesis of Shinrin. Thank you for your attention, and I hope you enjoy my proposal for the Retrosynthesis competition. I want to thank Sociedade Portuguesa de Química for the free attendance and the Portuguese Science of Technology Foundation, FCT, for the PhD grant. Any questions?
Obrigada, Patrícia. Vamos deixar as perguntas para o final, para a apresentação para o júri, está bem? E passamos agora à segunda apresentação do grupo M&M's, da Faculdade de Ciências e Tecnologia da Universidade Nova de Lisboa, constituído pela Ana Sofia Santos, o Nuno Vidoedo e o Diogo Poeira.
Boa tarde a todos. só partilhar o meu ecrã. Okay. Okay. Good afternoon, everyone. My name is Diogo Poeira, and I'll be presenting on our proposal for the synthesis of Shinrin on the behalf of my team, also composed by Ana Sofia Santos, who gave a talk yesterday, and by Nuno Vidoedo, who also has a poster in this conference. First of all, I would like to briefly introduce some key points of the target compound for this competition. So Shinrin is a marine metabolite belonging to the Mycosporin family. It was first isolated from Pateria pectinifera, a species of starfish indigenous to Japan and China seas. This compound is shown to have a strong ultraviolet absorption maximum, and as such is used as a key active ingredient in sunscreens. Commercially used, Shinrin is isolated from red algae, and there still is no reliable method for the chemical synthesis of this compound. Synthetic studies towards mycosporins were reported by James D. White, and although he never achieved the synthesis of this compound, his results were a major advancement toward the total synthesis of this type of compound. So first, I would like to present a simplification of the retrosynthesis that we proposed. First, the disconnection of the serine amino acid leading to the conjugated ketone represented. We also added protecting groups for both the alcohols and the carboxylic acid. Next, the disconnection of the glycine amino acid should be done either left or right of the nitrogen atom. In this sense, we propose both the insertion of the entire glycine moiety or the construction of this amino acid after installing the nitrogen. Lastly, the disconnection of the methyl group, removal of the ketal protecting group and functional group interconversion to give us chilic acid, our chosen starting material. So this compound was chosen due to being a fairly cheap natural product, having the desired chirality and being relatively similar to the desired product, overall requiring a low number of synthetic steps. For the challenges of the starting material, this compound has rigid selectivity issues since the secondary alcohols are almost chemically identical. The formation of the imine via ketone condensation can also be problematic. One of the most difficult aspects of the synthesis is its potential to aromatize, especially after oxidation steps. And since these compounds easily absorb light, it is also expected that all intermediates should be light sensitive. With this in mind, we propose the following synthetic strategy with 8 steps towards an intermediate 2, then 2 to 4 steps towards the intermediate 3, and finally 3 steps towards the final product. For the synthetic strategy, we propose 2 methods for the synthesis of 2, method A and method B. For method A, we start with a protection of the vicinal alcohols in the right, using benzaldehyde and acid catalysis. This also leads to the formation of a lactone bridge. Next, the opening of the deoxy ring using N-bromosuccinimide and an azo starter for the formation of the brominated compound. Removal of the benzoyl group should be achieved with the use of potassium carbonate in methanol. And while the lactone is also susceptible to methanolysis, we believe that this moiety should hold. Methylation of the secondary alcohol should be achieved selectively through the use of sodium hydride and methyl iodide. Next, the reduction of the lactone with sodium borohydride should give us the reduced product, which is immediately protected to form a ketone. Oxidation of the secondary alcohol should be achieved through Svern reaction. Immediately followed by elimination of the bromide to give us intermediate 2. Since triethylamine is both used in the Svern and elimination reaction, we also suggest that both these reactions could be done in a single step. To sum up, the major advantage of this method is the methylation of the desired alcohol. However, the main challenges here are the scalability and sustainability of step A2, due to the use of benzene and a radical starter. The deprotection of the benzoyl group in step A3 could also lead to the opening of the lactone. Step A4 could lead to the formation of an epoxide, and this is all assuming that the bromine atom holds for 5 synthetic steps, which is also a possibility. We also propose a different method for obtaining the same intermediate. First, the formation of a lactone using para-toluene sulfonic acid, followed by protection of the vicinal alcohols using trifurgen. Reduction of the lactone using sodium borohydride should give the desired product without affecting the carbonate. Afterwards, protection of the vicinal alcohols using a ketol and Swern oxidation should give the desired ketone. This carbonate is then selectively deprotected using basic conditions. And in the following step, the methylation is achieved through the use of silver catalyst and methyl iodide. This method was found to be a selective methylation for the alcohol adjacent to a ketone. And although the substrate is different in the reported method, we also believe that this reaction should be selective. Lastly, reaction of the resulting alcohol with triflic anhydride should give a good leaving group for elimination. To sum, the major advantage of this method is that we do not have a bromine atom, therefore elimination and aromatization should not be an issue. As for challenges, the reduction of the lactone without affecting the carbonate could be an issue, and the selective methylation of step B4 could be a deciding factor for this method. With 2, we must now install the glycine moiety. The first step is a bromination of the double bond, followed by elimination to give an alkenyl bromide intermediate. From this alkenyl bromide, several reactions can be performed. One of the pathways that we propose is the reaction with azide, followed by reduction to give an enamine. This enamine can also be obtained in one-pot manner with stepwise addition of the reducing agent for the azide. Reacting this enamine with a bromoacetate should give us the desired intermediate 3. While the enamine should be less reactive than the corresponding amine, this reaction is shown to give quantitative yields even when an aniline is used. Alternatively, reacting the alkenyl bromide with the glycine ester hydrochloride could also directly give intermediate 3. Should both these methods fail, we also suggest a Staudinger reaction to give the iminophosphorane, which can in turn react with glyoxylate via azavitic to give an imine. The resulting imine can then be reduced with cyanoborohydride to give intermediate 3. This reducing agent was chosen to avoid possible reduction of the conjugated ketone. Okay, to sum up, the major challenges here are the lower reactivity of the enamine in step 16. Basic conditions can also lead to elimination and aromatization of the intermediates. Also, should step 15 be performed, the possible reduction of the carbonyl could also be a problem. Okay, finally, the last steps of the synthesis, the ketol in intermediate 3 should be removed under mildly acidic conditions. Assuming that the target imine is susceptible to basic deprotecting conditions, we propose that the ester be deprotected first using lithium hydroxide. To form the imine, if we have selected various possible conditions for the condensation, we propose reflux conditions in ethanol, although there is a strong possibility that the high temperatures can lead to starting material decomposition. We also propose the use of titanium chloride at a lower temperature. However, this could lead to other problems, such as the contamination of our final product with titanium. On the other hand, should the imine product be compatible with hydrolysis, we suggest that these steps be reversed, with first the condensation using serine methyl ester hydrochloride. We also suggest in this step one of the mentioned conditions, as well as the use of boron trifluoride. These condensation reactions should also be performed using a desiccant, such as molecular sieves, in the case of a reflux reaction, using an azeotropic distillation method. To finish, the hydrolysis should be performed using the already mentioned lithium hydroxide method. To sum up, the major challenges in the final part of the synthesis is avoiding aromatization, especially in the condensation reaction, which could require harsher conditions. Also, both the glycine and serine amino acids are susceptible to hydrolysis, and as such, attention should be given to this possibility. Another major challenge is the possible incompatibility of these intermediates with reflux conditions, and also the use of titanium chloride could lead to the contamination of the final product. Although we do not propose any method of this type, we also suggest that a condensation could be done using a chemoenzymatic method. To finish, I would like to thank everyone involved in this proposal, especially my team members, Ana Sofia Santos and Nuno Vidoedo. I would also like to thank SPK and BL for creating this contest, as well as the organizing committee of PYCHeM.
Muito obrigada, Diogo, por cumprir o tempo. Passaria a pedir-lhe que descompartilhasse e passaria agora à equipa metiletilpropil da Universidade de Coimbra, que é constituída pelos elementos Alexandre Felgueiras, Vitali Masli e Zoe Moreira. Penso que pronunciei bem, Zoe, e pedi ao Zoe para compartilhar agora o ecrã. Estão aí os três, já vos estou a ver.
Boa tarde.
Boa tarde.
Boa tarde. Boa tarde. Podem então dar início à vossa apresentação.
Pronto, a partida já consegue. So hello everyone, my name is Zoe Arnaud. I am here with Alexandre Felgueiras and Vitali Masli for representing the team methylethyl-propyl for the first competition of retrosynthesis organized by the Portuguese Society of Chemistry. The molecule that was proposed for this competition was Shinrin. Shinrin has this structure. It is a mycosporin-like amino acid that works as a sunscreen for beings that live in areas with very high sun exposure. It is capable of absorbing UV radiation in a wavelength range of about 310 to 365 nanometers, and it is used commercially as a formulation in skincare and cosmetic products known as Heliogard 365. This class of compounds is produced by algae and bioengineered bacteria with low selectivity for Shinrin and difficult purification of each compound. Here on the right, you can see an example of the biosynthetic pathway. In green are represented enzymes that you can see are quite a lot in this biosynthesis. This molecule is quite complicated, so it is necessary to do a retrosynthesis analysis to be able to try and do the best synthetic pathway. Retrosynthetic analysis is a technique used for solving problems in the planning of organic chemistry and synthesis. It was firstly formalized by Elias Corey, who won a Nobel Prize for chemistry in 1990 thanks to this. It allows chemists to work in reverse by breaking up complex targets and obtaining commercially available precursors. And it also allows us to try and understand which retrosynthesis is best to be able to synthesize the molecules with cost-efficient simplicity and feasibility of the compound. The most favorable and efficient route can then be chosen before the synthesis is started. In the case of Shinrin, we can observe that there are several cythins that are possible to be obtained. In our case, we chose to first remove the amino acids, which are the serine and then the glycine from the molecule. Which allows us to obtain this particular compound. This compound is interesting because it is an achiral molecule, and because it is achiral, we don't need to worry about the stereoselectivity for the rest of the synthesis, which facilitates it quite a lot. After obtaining this compound, we can insert this methoxy group. based on this particular molecule. This molecule, when it suffers an Nmr rearrangement, it gives us an amine derivative. From the amine derivative, we can insert the methoxy group through an intermediate of diazonium. Then for the synthesis of this compound, we can observe in the literature that these are quite simple modifications. And from the butadienoic acid, we can do a bromination and a esterification, obtaining the necessary molecules to be able to synthesize this particular compound.
As shown here in this slide, this is the general synthesis proposal that we have done. The synthesis proposal has nine transformations, and we divided it in 7 different steps. The first step is the bromination and esterification of the butadienoic acid. This reaction is described in the literature, and the first step has around 80% expected yield. The resultant compound can then be esterified in a simple reaction, obtaining the compound 1.2. This compound can then be cyclized with methyl trioxybutanoate. This reaction is also reported in the literature and consists in 2 steps. First, the cyclization proper in very basic conditions in reflux. Then the resultant cycle is hydrolyzed and decarboxylated under water. The resultant compound 2.1 has an expected yield of 28%. This cycle can then be transformed into the corresponding Eycm through treatment with hydroxylamine in methanol in the presence of a base. Then the Eycm can be tosylated in low temperature, and the correspondent compound is immediately and in situ transformed into the intermediate azurine through a base catalysis. This azurine can then be simply hydrolyzed in normal conditions to obtain the compound 3.4. This reaction has around 60 to 95% expected yield. The correspondent compound 3.4 amine can be transformed into the diazonium ion through treatment with sodium nitrite in acid catalysis in methanol. The compound 4.1 is immediately attacked by the methanol, the solvent, and we can obtain the compound 4.2.
Next, we can hydrolyze our bromide groups. For that, we use iron bromide as a catalyst. Although trees look like a simple reaction, it may cause some problems. Such problem may be the elimination of bromides or the hydrolyzation of the methoxy group. To lower the side products in this reaction, strict control over temperature need to be established. Then we can purify our compound 5.1 using an base water extraction. As you may see on this theoretical graphics that was calculated on the side below, our starting compound is insoluble in water, while our compound 5.1 is soluble in basic water. So doing an extraction, we can isolize our compound 5.1. Then lowering the pH, we can get our compound to precipitate. After, we can proceed with the addition of the amino acids. We decided to start with the serine because it's a chiral compound that we can buy commercially in a chirally pure form. Reacting with our compound 5.1, we get 2 diastereomers. The RR version, that is the desired one, and the SR. We expect no selectivity in this reaction because the ketone groups are quite similar. Then our undesired compound SR, diastereomer SR, can be transformed back to the starting material using acid catalysis. Repeating several times, we can increase the sustainability of our reaction and get a higher yield. After we get our compound 6.1 with RR chiral groups, we can proceed with the addition of the glycine. It's a simple reaction with the same conditions as the previous one, getting our final compound 7.1 that will isomerize for the target molecule Shinrin.
As for the final remarks, our synthetic procedures are quite simple. High yields are expected at most steps. Because we're using natural amino acids from the chiral pool, we also expect to have very few problems in stereoselectivity throughout the synthesis. We also expect efficient diastereomer separation, as mentioned in the last few steps. Our synthesis also avoids expensive and asymmetric synthetic methods, which is very important to have a cost-efficient synthesis. It also presents flexibility to synthesize other microsporin-like amino acids that have the same cyclohexanone core. So other compounds can be used by just changing in the last step the amino acids that are substituted. We also have quite a lot of steps where green chemistry is used, as we chose to use rather ethanol and ethyl acetate instead of chlorinated compounds and chlorinated solvents. We also use renewable catalysts, such as iron 3 bromide, which are very good also for the green chemistry aspect of this synthesis. If you would like to know a little bit more about the steps that we present here in this work, these are the references that we used. We are now available to answer any questions. Thank you for your attention.
Ora, muito obrigada ao grupo metil-etilpropil e passamos agora à quarta apresentação e última do grupo Retrogirls da Faculdade de Farmácia da Universidade de Lisboa, constituído pela Lídia Alexandra Santos Cavaca, a Mariana Jaló, a Juliana Pereira, a Rita Jesus, o João Arravasco.
Olá, boa tarde. My name is Mariana Jaló, and along with the Retrogirls, we are going to present you our proposed total synthesis of Shinrin. So, for the total synthesis, we envision to divide this synthesis in 4 steps, in which we can have an influence not only by the work developed in Carlos Afonso's group, but also by the synthesis of Stalmivir that was designed by Curry. Okay, so for the first approach, we propose an asymmetric dialder with a derived proline catalyst to form compound 17. And then upon glycine reaction, we can undergo a neodolactimization followed by an allylic bromination to attain compound 12. Afterwards, for the second stage of the reaction, we can have an epoxide that is selectively formed in this position, and this is because of the presence of this electro-withdrawing group here. And afterwards, opening of the epoxide can be achieved in acidic conditions using the reagents here present. Only then we can reduce the ester to then protect the alcohols to attain this final molecule number 8. So the third stage is characterized by a sharpless asymmetric dihydroxylation to form compound 7 with an expected yield of 85%. Then NO-acetal can be formed using benzaldehyde in the presence of copper triflate. Afterwards, we can also apply an severe oxidation conditions to attain the ketone, number 5, with an expected yield of 97%. Okay, so then we envision that the opening of the NO-acetal can be achieved in slightly acidic conditions, and then incorporation of protected serine to attain the ketone 3B. It is important to notice that the ketone can be in equilibrium form with the enolic form, and also we can attain a compound 3A. Only then 3A can be converted to an alcohol, can be methylated in the alcohol position to attain compound 2. And finally, by removing the protecting groups TBS and BOC, we can attain the desired compound Shinrin. So as a summary, we propose a synthetic approach for the total synthesis of Shinrin in 4 stages with an overall yield of more or less 30%. So the first stage is characterized by the Ultrasound synthesis that is already known in the literature, and also we decided to include some of the reactions that we are performing in Professor Carlos Afonso's group. We thank you very much for your attention, and if you have any questions or comments, please feel free to do so.
Muito obrigada, eu penso que estamos bastante bem no tempo e agradecer também mais uma vez a este grupo por ter cumprido o tempo previsto. E eu passaria agora a palavra ao júri, pedia para vocês descompartilharem a tela e começaria por ser presidente. Não sei se querem colocar algumas questões às várias equipas. Professor Artur Silva, passa a palavra.
Ora, boa tarde a todos, muito obrigado pelas excelentes apresentações, cumprimentar as senhoras duas chefes deste processo todo, que foram elas que são as mentoras, nós estamos aqui, Emília e Paula, e agora nós temos uma perguntinha organizada para cada um e depois, se o tempo der, ainda podemos fazer mais uma outra, mas agora, e por isso eu ia pedir à Teresa Pinhamelo para fazer a sua pergunta.
Sim, portanto, eu ia começar então pelo primeiro grupo que apresentou. É uma apresentação de uma pessoa, não é? Neste caso não é de um grupo, da Patrícia, não é? Penso que me está a ouvir a Patrícia, não é?
Sim, então.
É um comentário e depois uma questão curta. Portanto, eu gostei da sua apresentação e o seu trabalho muito completo. O meu comentário é que, efetivamente, as propostas apresentadas eram muito próximas do que é conhecido na literatura. Portanto, relativamente a outras propostas, depois é difícil de avaliar o seu contributo para a estratégia que é apresentada, em termos genéricos, não é? Portanto, isso é um comentário genérico. Na sua apresentação, não sei se se apercebeu que é a primeira via que diz mesmo que é a mais próxima da literatura, não é?
Sim, sim.
Depois aparece lá um grupo sulfona, mas no texto chama-lhe sulfinato. Viu efetivamente, teve o cuidado de ver qual era essa transformação. Não sei se se apercebeu que a estrutura no artigo original estava escrito de forma abreviada, imagino que possa ter induzido em erro, mas está a ver qual é a sequência, não é? Na primeira sequência há ali vários passos que apresenta ali como um grupo sulfona, não é?
Sim, portanto, a sua opinião, sim.
Provavelmente não se apercebeu que realmente não era esse o grupo que os autores descreveram, está bem?
Ok.
A única coisa que eu
tenho que confirmar, mas
era o seguinte: fez um esforço enorme para fundamentar as várias propostas alternativas, porque tem duas vias e depois tem ainda propostas alternativas, que pode ser um ponto positivo, mas pode ser um ponto negativo que torna menos clara a apresentação, não é? Mas, de qualquer forma, depois organizou no seu trabalho escrito até várias tabelas e apresentou também os exemplos aí na sua apresentação, que era comparar a transformação que queria fazer e um exemplo da literatura para fundamentar, não é?
Sim, acho que era o que era pedido, não é?
E eu, olhando para um exemplo em concreto, é a transformação de 7B para 8B, que era o que identificou como uma ESN2, não é? Com a inversão de configuração, portanto, descreveu
Sim, neste caso usei esse protocolo, mas neste caso a nossa molécula, aquilo não é aromático, comparado com...
Que eu tenho, portanto, se for escolher um exemplo, que tipo de transformação é que tem no exemplo que foi escolher para suportar essa sua proposta?
Sim, eu escolhi neste caso um protocolo que sim, tem uma quinolona, se não estou enganada.
É aromática. Para ilustrar até a inversão de configuração não foi a melhor escolha. Portanto, este é um exemplo e há algumas situações deste género, não é? Mas, portanto, globalmente penso que foi um esforço meritório, portanto tem ali e realmente revelou, e muito cuidado na apresentação escrita e na apresentação oral.
Ok, muito obrigada.
Nesta fase.
Obrigado, Teresa. Agora passava o Augusto, que vai perguntar a M&M's.
Boa tarde a todos. Queria dar os parabéns também às 4 equipas que passaram esta fase final e em particular ao Diogo, que acaba de fazer dos M&M's, acaba de fazer agora uma perguntinha sobre um comentário. O vosso trabalho está bem organizado, tem algumas alternativas para eventuais problemas que possam surgir, ou vias alternativas para um composto. Não encontrei assim erros graves, ao contrário de outras propostas. A quiralidade dos compostos também está justificada, percebe-se bem de onde é que vêm os centros quirais. Por isso não há assim nada muito problemático. Queria fazer uma pergunta um bocado genérica, que é da vossa via de síntese, que é bastante longa, depois já na concretização, na via de síntese há muitos passos. Quem faz química orgânica está habituado a alguns no tempo, aparece um percalço, que é mais difícil de resolver, às vezes obriga-nos a voltar tudo ao zero. Nesta vossa proposta, qual é que vocês acham que é o passo que pode dar mais problemas e porquê?
Ok, se me permite responder, eu acho que falo pelos meus colegas quando digo que acho que o passo mais difícil desta síntese toda será a formação da imina. Portanto, a adição da serina, o passo final ou o passo antes do final, caso escolhermos desproteger antes ou depois, acho que será o passo-chave de toda esta síntese.
Está bem. Ok. Obrigado.
Tá bom, Augusto, obrigado. Obrigado à equipa também. E agora passava a Amparo, que vai fazer um comentário para o Meteu, é teu para o Pedro.
Eu já agora aproveito também por dar os parabéns às equipas que chegaram à final, mas também àquelas que ficaram pelo caminho, porque isso significa que temos jovens químicos interessados e com vontade de aceitar um desafio. Não era um desafio fácil de todo, por isso foram 9 equipas e por isso estão todos também de parabéns. Relativamente à equipa metilipropilo, apesar de terem escolhido o nome do início, com poucos átomos de carbono, não foi assim tão trivial e tão simples a proposta. De facto, é uma proposta que sai fora, como vimos, um bocadinho fora da caixa, por assim dizer, que apresenta propostas interessantes, mas eu gostava, de facto, já agora, que me explicassem aquela última etapa. E é nesse sentido a minha pergunta. Quando tem um derivado 6,1, se quiserem partilhar, depois quando colocam a glicina, gostava que me explicassem um bocadinho melhor como é que acham que chegam à shinurina com essa...
Partilha. Ok, podemos partilhar o ecrã para ser mais claro, talvez? Aqui está.
Posso explicar?
Ainda não estamos a ver, agora já está.
Agora sim.
Suponho que a dúvida está no último passo, que era precisamente a isomerização, correto?
Sim.
Ou era a adição?
As duas.
As duas. Pronto, a isomerização de facto pode acontecer um bocadinho mais cedo, mas no entanto não intervém com a nossa reação, com a nossa síntese. Isto é um equilíbrio, basicamente, entre, tal como nas cetonas, um equilíbrio cetenólico. Assim, quando nós adicionamos, este próton é muito ácido, nós adicionamos uma amina, ela pode transformar-se numa amina secundária, e o mesmo acontece ou aqui no último passo, que nós indicamos como isomerização, ou então aqui, quando nós adicionamos a serina. Mas, no entanto, tal como depois temos a cetona de qualquer maneira, não decidimos que não vale a pena indicar agora, indicamos como último passo. A adição é simplesmente uma adição de uma amina primária a uma cetona que, pronto, forma amina.
Ok.
Não sei se está claro. Também esta isomerização das ciclohexadionas é relatada na literatura naquela referência. Especificamente este tipo de isomerização das enaminas.
Mas tem o exemplo que é dado não é uma amina primária. uma arilamina.
Sim.
Não é? Já agora, e em termos da estereoquímica do aminoácido final, face ao composto que era pretendido?
Relativamente ao 6.1 ou à Shinrin em si?
O 6.1 dá origem à Shinrin, certo?
Certo.
E se vocês repararem, virem a configuração absoluta,
Está certo.
qual é a configuração absoluta aqui?
É RR.
E na Shinrin?
Também é RR.
No composto que vos era apresentado. Aqui está certo. E no composto que vos foi proposto fazerem a síntese.
Então ao contrário. Foi, ok, já estamos a ver.
Sim.
Um erro de representação. Enganámos na estereoquímica da serina específica aqui. Porque não é R, é S. É L, mas é L serina. Foi mesmo um erro de representação. Ficou mal desenhado.
Ok. Não tira qualquer mérito, está bem?
Sim, mas agora...
Mas é uma falha, de facto.
Estamos a ver o erro, sim.
Está bem? Não, pronto. Era só.
Obrigado. Podem parar
obrigada.
a partida. Podem parar a partida, se faz favor. Obrigado. E agora passava a Matilde para fazer a pergunta às Retrogirls.
Às Retrogirls. Ora bem, muito boa tarde. Eu faço minhas as palavras dos meus colegas. Foi com muito gosto que eu vi estas vossas... primeiro as vossas propostas e agora as vossas apresentações. Acho que estão todos de parabéns, foi um esforço muito grande e é muito bom realmente nós vermos jovens químicos interessados em síntese, que é uma coisa, retrossíntese e síntese, obviamente, que é uma coisa cada vez mais rara porque a síntese dá muito trabalho, não é? E portanto é um gosto nós vermos que temos aqui pessoas que vão, enfim, continuar este esforço. Ora bem, em relação às Retrogirls, eu achei a vossa proposta também um bocadinho fora da caixa, visto que tentaram fazer from scratch e não ir à Chiral Pool, não é? E portanto isso foi à partida bastante interessante. Eu tinha aqui uma ou duas perguntas e a primeira é logo sobre a vossa iodolactinização, ok? Porque vocês inspiraram-se na síntese do Corey. O Corey tinha um grupo, creio que fez com NH3, não é? E, portanto, a primeira adição, e, portanto, a iodolactamização era relativamente, mecanisticamente trivial. Vocês acham que a introdução do aminoácido aqui nesta fase tão inicial poderia dar problemas?
Sim, ou seja... Está ligado. Desculpa, ia começar a falar inglês.
Podemos falar inglês.
Com as condições que temos, ou o facto de termos o ácido, poderia haver a desprotonação do ácido, portanto a nossa proposta seria talvez utilizar um pouco de excesso de base para garantir também para garantir que também seria feita a reação que nós pretendíamos. Depois penso que o mecanismo seria via formação do sililenoléter e depois a abertura do íon iodónio que seria formado na dupla ligação.
Ok. Já agora, se ainda tenho tempo para fazer mais uma, a vossa epoxidação tem a certeza que é regioseletiva?
Sim, temos. Nós vimos um artigo na literatura que dizia que mesmo havendo outra dupla conjugada no composto, ela era seletiva para aquela dupla que era adjacente ao éster.
Ok, pronto, é que depois não justificaram creio que não justificaram no vosso, na vossa proposta e portanto, põe-se sempre, essa questão é sempre uma curiosidade. E já agora só uma última muito rápida, e na vossa de hidroxilação de Sharpless, a estereoquímica, também estão confortáveis com ela?
Acho que sim. Nós estamos confortáveis com a estereoquímica. Obviamente que isto na bancada a conversa é outra, não é? Mas seria uma tentativa e nós propomos isto porque idealmente nós necessitamos ter este hidroxilo nesta configuração para poder fazer o
Pois, exatamente.
E nós achamos que os cápsulas aqui nesta dehydroxylation é o melhor approach, por assim dizer, para conseguir obter este composto.
Pronto, é como a Mariana diz, isto às vezes na bancada não é bem assim, mas o esforço está cá e portanto, muitos parabéns, eu gostei bastante da vossa proposta, achei muito interessante. Ok, muito obrigada.
Bom, eu acho que estamos a chegar ao tempo também, faltam só os 4 minutos, acho que não vamos fazer mais questões. Bom, o que nós demos para mostrar é que logicamente que aqui o que interessa e que foi o objetivo, acho que da Emília, da Paula, é mostrar que há jovens portugueses bastante interessados em química, neste caso, como a Matilde disse, em síntese e em retrossíntese, porque é muito trabalhoso e às vezes é mais fácil fazermos outras coisas. Realmente aqui as estereoquímicas às vezes, como esta do Sharpless, os dois OH podem não ir para aquela posição, podem ir para a posição contrária, se não tiver lá um composto que irá lá ajudar ou a fazer alguma coisa mais. Mas bom, é isto que vale, nós também os mais velhos, também se fizermos retrossíntese, etc., também não acertamos elas todas. Isso acho que foi um trabalho interessante para todos, como já acho que foi o Augusto lá par que falou, os 9 grupos que nós tivemos desde o princípio. O júri gostou muito de ver, de analisar. Acho que ficámos todos mais ricos e todos os que assistiram a esta sessão também. Gosto de ver aqui estas caras novas, que eu conheço algumas, outras não. E por isso, Paula e Emília, acho que vamos cumprir o tempo, por isso estamos no tempo normal. Agora a seguir, depois quando nós saímos desta sessão, nós os 5 vamos fazer outra sessão para tomarmos a decisão final, já está. E depois então no final do dia, na sessão de encerramento, lá estarei para anunciar quem é o vitorioso, mas eu acho que vocês já são vitoriosos todos porque fizeram esta apresentação, fizeram este trabalho de enriquecimento e por isso estão de parabéns todos.
Muito obrigada, professor Artur, muito obrigada a todos os elementos de júri, isto acrescentou aqui muito o desafio hoje. Nós, antes de darmos por terminado, o professor já esclareceu, irão deliberar e anunciar antes da sessão de encerramento, o vencedor. E nós, eu e a Paula, gostaríamos de agradecer a todos, mais uma vez, elementos do júri, muito obrigada por toda a colaboração. À empresa farmacêutica Bial pelo apoio, pelo patrocínio, na pessoa do Dr. Paulo Vital, que estamos a vê-lo aqui presente, muito obrigada. À organização do 7º PYCHeM, não só pela colaboração e oportunidade em realizar aqui esta sessão que é tão apropriada, mas também pelo sucesso, parabéns pelo sucesso deste 7º evento, assim, nestas condições à distância. E teríamos uma palavra final para todos os candidatos, pelo desafio que aceitaram, que hoje vimos que ainda foi maior, com a qualidade do júri também que se apresentou, mas pela elegância das propostas apresentadas e a vossa maturidade na apresentação. Parabéns, só podemos fazer votos numa próxima edição tão profícua e eu, em nome meu e da Paula, agradecer a todos e daremos assim por terminada a sessão.
Obrigada a todos.
Obrigada.
Parabéns.
Obrigada a todos.
Parabéns.
Ok, então nós...
Thank you so much to the people involved in this first Retrosynthesis award competition. It was very fruitful, I hope, and good luck for those who are now expecting the results. let the best one win, as they say. So thank you, Professor Paula, thank you, Professor Emilia, and the remaining jury of the competition. We will now go to the coffee break poster session. Just a small reminder, this is the last option for those who wants to vote in the 3 best posters. In the end of the session, the posters will be removed from the website, and we will begin the counting of the best posters. So we will see you at 4:45. So see you soon and enjoy the coffee break. Thank you. Thank you so much.
Boa tarde.
Olá, boa tarde.
Ana e Ricardo, tudo bem?
Tudo bem.
Estamos agora live no YouTube, enquanto estamos a aguardar o início da próxima sessão.
Sim.
Portanto, tudo aquilo que nós dissermos aqui está a passar também no YouTube, está bem?
Está bem, está bem.
Vamos aguardar o início da sessão, está bem? E depois
Muito bem.
Assim, está bem? Muito prazer em conhecê-la.
Igualmente.
Então,
Obrigada.
até já. Com licença, até já, até já. Hello, good afternoon, everyone. Welcome to the last session of oral communications in the 7th PYCHeM, on the last day of the 7th PYCHeM. So without further ado, I will move on the word to Professor Ana Ricardo, that will be the chair of this afternoon session. So Professor Ana, whenever you want, you can start. Thank you so much for your presence. Enjoy.
Thank you.
Thank you so much.
I'd like to congratulate all of you.
Thank you so much, Dr. Ana Ricardo, for your chair of this session. It was very fruitful, and thank you to the oral communicators. I think that Anna wants to talk, or okay, no, it was an applause. Okay, so thank you so much. Congratulations to all of you, and thank you again, Dr. Ana Ricardo. So let's move on to the next session of this afternoon, that will be moderated by Márcio Carocho. So I will pass on the word to you. Thank you, Márcio.
Hello, good afternoon. Thank you very much, Inês. It's a pleasure and an honor to be a moderator of this final session of this 7th PYCHeM. We are going to go through two presentations pertaining to the Young Chemists Network. Then we are going to hear a presentation from the Portuguese Young Chemist Award. And finally, we are going to see who won the Retrosynthesis Award. So without further ado, I would like to introduce Maximilian Menche, who is the chair of the European Young Chemists Network. And he will be giving us a speech about this network and how it has been going. Please, Maximilian.
Yeah, thank you for the kind introduction. Let me quickly start sharing the screen. Okay, yeah, so thank you for the opportunity to present the European Young Chemists Network here, the EYCN for short. So maybe let's start with who we actually are, if the slides actually move. There we go. So we're a network of various European young chemist networks. And so, of course, also the Portuguese young chemists are very much involved here. And this also means that with the roughly 30,000 members that we are representing and that send 42 delegates from these 31 societies that I have just shown, you, if you are a member of the Portuguese Young Chemist section, are already also a member of the EYCN and should really consider to use the available materials and events also to further connect and educate yourself across Europe. So since this March, I have the honor of being the chair of the European Young Chemist Network with this fantastic set of colleagues helping me. And what we really are happy about is that in these 8 board positions, we're able to represent 7 different countries and national societies. And we actually have 5 women and, well, just 3 men on our board of 8 people. And even more promising, I think, is that the EYCN has managed to maintain this actually over the 15 years of the existence of the EYCN, where the number of males and females have pretty much been 50-50 throughout all years, and actually the all-time average of board members is also above 50% female. So what are we doing as a board and with our delegates and for all our members? So first of all, we want to exchange ideas and projects between the Young Chemist networks. So really have the networks that maybe are existing for a bit longer help out newer networks and smaller networks, and whether that is also with helping to provide funding or whether it is just with experience and on events and formats that work really well. But besides just these societies, we also, of course, want to promote the exchange of knowledge and enable networking opportunities for early career researchers directly, and not just the societies. And with that also provide mentoring and support to everyone that is searching for it across Europe. And then maybe a bit different to the other three goals, but really important as well, is of course improving the visibility of chemistry, maybe also outside of the chemical research field, and outside also of chemical industry, but really go to the general public, where chemistry sadly is often just seen as toxic and bad, and not as also as the opportunities and solutions that chemistry provides. So one of the projects that I quickly want to talk about today is chemistry across Europe. It's a project we started quite a few years back to increase mobility across European countries. And of course, in the last 1.5 years, that has been very tough. But what it is a map that when you look at it and when you click on any country on this map, for example, in this case, France, you will actually get detailed information on how how studying in that country is actually working, when the semester starts, how much the tuition fee is, what language you might need to be able to speak, and so on. So anyone that is looking to go abroad during their studies might have a look at this on eycm.eu/map. And this is also being extended to feature specific universities and companies from all the countries across Europe. So you can kind of just find information on the country itself, but also maybe on a specific university that you really wanted to go to. So really have all the information in one place. Then, of course, due to COVID, we also had to change a lot of formats into online formats and webinars. I will not talk about the first column here because this is a cooperation with the Eycm, and Joao will present these right after my talk. But what I want to talk about is the Catalysis talk series. This is a collaboration with the Young European Catalysis Network that we have been doing. And we've just hosted the 20th session on this Wednesday. And besides, let's say, quite established speakers, or very established speakers like David Cole-Hamilton, Francis Arnold, and Bob Grubbs, who have given presentations, we also really wanted to provide an opportunity to young researchers like PhD students, like postdocs, and really young group leaders to present their research while all conferences have been canceled and normal presentations usually aren't possible. And then last but not least, we also had a replacement for the sadly postponed UChem's Chemistry Congress that was supposed to happen in 2020 in Lisbon and was moved to 2022. But we wanted to keep working on these important mentoring workshops, grant writing workshops, to really continue to provide support, especially in such a difficult time, and not cut this. And for most of these soft skills workshops, you can actually find them on our YouTube, which you can find at eycm.eu/YouTube. Another collaboration that we have done with the Eycm, and more specifically also with the German Chemical Society, is the topic sustainability in education. So first of all, we did a survey that attracted around 500 or above 500 responses from 45 countries, and found quite a high demand of students asking for sustainable chemistry in education, and claiming that they don't feel prepared to actually tackle these challenges in their work, especially also, for example, when moving to industry, where these are highly thought topics. And what we then did also was a webinar together with representatives from various networks like NESI, and then also NGOs like Beyond Benign, but also teaching with David Cole-Hamilton, and also bringing the industrial side in there with Evonik to present and discuss these results. And also this session you can find on our YouTube channel. Speaking of sustainability, we've also been contributing to last year's European Research and Innovation Days hosted by the European Commission, where we've participated in a session called Sustainability by Design, where we really tried to advocate for policymakers to also consider early career researchers and the opinions of the younger generations in the policy process. One more project that was quite suitable to start during the pandemic is the Eycm Podcast. So if you're rather looking for something different than webinars, but rather for a podcast while you're driving to work or driving home, there's already 6 episodes out there on, for example, important topics like CO2 reduction, microplastics, but also some a bit more on the research side. And there's more on important topics like electrochemistry, 3D printing, polymer recycling, and so on, coming hopefully very soon. And then this is, I think, a really important project and also a very important topic. And that is that this year we are hosting our 3rd Chemistry Discovered video competition together with the Wilkinson Charitable Foundation. And the topic is safety in chemistry. So you are asked to send a 90-second video with up to 3 friends or alone that is hopefully as creative as possible and will really show some aspect of safety in chemistry, because I think this is a very important but sometimes too neglected topic. And it's probably not the surprising prize for someone in Portugal, but the prize is a trip to Lisbon to the UChem's Chemistry Congress in 2022. So yeah, for you that's probably not too far, but for some, I think it's a really nice trip to a fantastic country. So some other projects we are involved in, for example, is UChem's policy workshops, and I picked this one even if it's a bit older one, because this one dealt with employability, so really also a topic very dear to early career researchers, I would say. Then we of course also have the European Young Chemist meeting, which also had to be postponed from 2021 to 2022 and is now scheduled to take place January 2022 in Freiburg in Switzerland. Then of course I had already mentioned this a bit throughout the talk. So of course we are working together with a lot of networks like the ACSN, the Chemist Committee, the Eycm, which we are really working together with a lot because they have very similar goals to us, I think, and Joao will say more about that in the presentation after this. And also the European Chemical Employers Group and the European Federation of Medicinal Chemistry and the European Federation of Catalysis Societies and their respective young chemist networks. So that's it from me. I think I'm quite well in time so that I can quickly, well, first of all, ask you to visit our pages if you're interested and want to learn more, or also feel free to contact me at chair@uycn.eu if you have any specific questions. And as let's say final thing, I would play this short video. I hope the sound works, which summarizes a bit what we are doing. Okay, so if there are any questions, I'm happy to answer them. And other than that, thank you again for the opportunity to give this presentation.
Thank you so much, Maximilian, for that brief presentation and quite in depth. I don't think there are any questions from the audience, but I would like to place a question and taking in consideration all the young chemists that are probably watching us right now throughout Portugal and throughout Europe, beyond these talks that were promoted probably even more because of COVID, what would be the main benefits for these young researchers, these young chemists, to take part in this big network. I mean, probably in terms of mobility, job opportunity. Talking directly to them, what would you say would be the most, what they could get out of this big network?
Well, I mean, you always, I think, have subtle benefits of expanding your own network. I mean, we have delegates, for example, that started just chatting in the evening at one of the events, and I think a few years later published that in quite high journals because they suddenly realized they are really could perfectly complement each other, and these are like always the small benefits of networking, right? That you might not instantly see, that you might not be able to predict, but having this network and then actually once you need it, realizing that you have already built it in the previous years is really helpful. And I mean, then of course, as you already said, there is lots of soft skills workshops where you can quite obviously learn something for your future career, as well as just stay informed and so on.
Thank you so much, Maximilian. I think there are no other questions. So now we will broaden this scope a little bit more, and we'll be listening to João Borges from the University of Aveiro, which is going to talk about the International Young Chemists Network. I don't know if João Borges is here. Oh, he is. The streaming is yours, please.
Oops. Okay, let me just put the pointer. Okay, so good afternoon to everyone from my side. I am João Borges. I am a researcher at the University of Aveiro. I am working mainly in the field of supramolecular chemistry, so developing supermolecular biomaterials for regenerative medicine. But today, and besides my scientific journey, I have been really very supportive of several Young Chemists network. I have started also within the Young Chemists group of the Portuguese Chemical Society. Then I have been also involved in the European Young Chemists Network, and I am still involved, that we just heard from Max. But today I'm talking about the International Young Chemists Network, as introduced by Marcio. And in there, so I am currently the chair-elect, so the vice president, if you may. And today I will give you like a glimpse of what we are doing in order to foment the contact, to connect and empower younger chemists worldwide. So who we are? So we are an associated organization of the International Union of Pure and Applied Chemistry. We are quite young. So we have just been created in 2017, where in Brazil, where we signed the Memorandum of Understanding with IUPAC. And of course, we have common goals, and we try to collaborate as much as possible with IUPAC in pursuing our joint goals. IUPAC provides us a lot of support technically, logistically, so it's really key in our development. And also, so several of our members are active in IUPAC, as well as in other organizations such as the Eycm, as Max mentioned. And our first General Assembly, so we meet every 2 years, was in Paris, so in 2019, in occasion of the IUPAC World Chemistry Congress. So as you know, also Professor Christopher Brett is currently the president of IUPAC. So we are very keen to collaborate also with him and the entire organization. So although young, so as I mentioned, we are created in 2017, we have really an international presence. So you can see here the world map of IOICN members that we span the 6 continents. And for any of you that is not aware and wants to join the network as a member, so you have here the eligibility criteria. So if you are doing your PhD, master or bachelor across chemical science, you are eligible to be part of the network. If you already finished, but you are under 35, you are also eligible. Or even if you have completed, for instance, your postdoc within the last 5 years, you are also eligible to be part of the network. One thing is the members, other thing is the delegates. So the delegates, we can have 2 per country, and normally they are nominated by the national adhering organizations that you can check them at the IUPAC website. And for instance, in the case of the Portugal, we have two that are linked to the Young Chemist group of the Portuguese Chemical Society. In this case, until in the last 2 years, it was André Seco and Karina Cruz. So also you have here the link to the membership form. So please go into there and check all the things that I have detailed here. So the eligibility, how you can join the different teams that we have. And if you have any questions, of course, you can email me or the network. I will show you in the last slide how you can contact us. So as I mentioned, in 2019, we held the first General Assembly in which we joined 43 delegates from 33 countries. Some of them joined virtually, of course, because not all can afford to attend meetings. In this case, it was in Paris, but of course, we have delegates from all over the world. And we defined the mission and the vision of the network. So the vision to connect and empower younger chemists at a global level, and the mission to support and advocate for younger scientists working across the chemical science towards a globally sustainable future. And here you have a picture of the delegates that were present live at IUPAC 2019 in the occasion of the General Assembly. Here I show the current executive board. So we have Laurie as a chair. She's an Australian, but she's living and working in the US. I am currently the chair-elect. Will be taken over as the chair in August in the occasion of IUPAC 2021 that will be held virtually, as we are now used to due to pandemic. Then we have the secretary, Funman from Singapore, Max, the treasurer from from Germany, sorry. And then we have 6 steering committees. Each of them has their own leaders, such as the finance team, led by Willis, the International Society Liaison, head by Torsten, the governance by Stephen, conference presence by Like, public outreach by Emiel, social media by Sebastian and Gabriela. And then we have also the webmaster that is also Gabriela, that is taking care of that, as well as our graphic designer that is Frank. So every 2 years we elect a new executive board in the occasion of the General Assembly. So again, prior to COVID, we used to go to conference. We used to present network in the form of the poster and talks, as you see here in Austria, in Russia, as well as we have participated in the International Year of Periodic Table, the official ceremony in the UNESCO headquarters taking place in Paris. Of course, we have the opportunity to chat with each other and to meet each other in the face-to-face manner. Of course, due to pandemic, we had to adapt and we had to pursue other initiatives, as it was also mentioned before. And of course, I think that this allowed us also to grow and to make us also, I would not say experts, but now we dominate much more the way that we can work with the media and take advantage of different platforms to connect with each other and reach to people at a global level. So we organized a series of workshops to support and empower early career chemists. Although this can be transversal to several areas, not only across the chemical science. And for instance, as you can see here, we have organized, for instance, a workshop on the diversity in career paths in chemistry, science outreach, scientific writing. We have organized many more workshops, and all of them are listed at IUPAC YouTube channel. So I ask you to please go there if you are curious about this, and you can listen to the recordings of all the webinars. And this allows us also to increase the reach of the people that we can reach, because although presential meetings are, of course, much better, but not all the people can afford to travel to different places due to financial status, health reasons, and so on. So this was one of the initiatives. Also, as Max mentioned before, so we have been partnering a lot with other young chemist networks, such as the UICN and the Younger Chemists Comment from the American Chemical Society. And this one, the Chemists Fighting COVID, was in fact it was our first webinar to organize together, and we got more than 700 people that attended. In that time, it was really a pressing topic, because it was really after people went home due to the pandemic. Besides, of course, we have organized all these webinars and others that, again, all of this is at IUPAC YouTube channel. So please go into there, and I am sure that will be enriched. This will be useful for your careers. You will learn a lot of soft skills that will help you grow personally and professionally. Also, together with IUPAC and on the occasion of celebration of the 100th anniversary of IUPAC and International Year of Periodic Table, IUPAC and IOICN have launched the Periodic Table of Younger Chemists, in which we have unveiled and recognized and 118 chemistry that represent different elements of the periodic table, and that they have been selected and honored due to their creativity, dedication, leading us to the next century of IUPAC. So all of them, or most of them, then met together at IUPAC 2019, in which they get together and met each other. Since we wanted to also to move forward with this project and give somehow a continuity, we create this project together with IUPAC that is called the Chem Voices. So we want to give a voice to these younger chemists that have been recognized in scope of periodic table of younger chemists. And we are organizing a series of webinars that we want to give them the light and put them on the scope to discuss topics that are of interest to them and in the broad sense to the overall scientific community. And you can go to this website, chemvoices.org, to learn more about these projects, as well as to see previous webinars and the new ones that are planning, that we are currently planning. Just to highlight some of them, so foster innovation through collaboration, the importance of diversity in science, science communication. So there are many more, and all of these again are at the chemvoice.org website, but also at IUPAC YouTube channel. So just to highlight the next one that will be taking place next week, so May 28th at 1:30 Central European Time. It's a webinar on leadership, and we'll be having 3 presentations from these younger chemists that will share their own career paths, as well as how they handle leadership and how they move forward in their careers. After their talks, we'll have a panel discussion in which you can make questions to them, and we'll be happy, of course, to engage you with the speakers. So please make sure that you can sign up. This is completely free, so you don't have to pay anything, as similar to the other webinars. So we are very welcome to join us. So besides this, we have been also writing several articles. So here I list just some of them. For instance, this one, a virtual journal in Empire Early Career Chemist, was a partnership with UICN. So you have here people in the authorship that belong to IOICN, UICN, as well as the Younger Chemists Committee of the ACS, and which we describe the events, the virtual events in which we have run over 2020. We have also a new article that was published very recently, also in Chemistry Reviews, how the delegates, how the younger chemists belonging to IOICN have been thriving, how they have pursued their goals, how they have moved forward, and how they have coped with the pandemic. So you can search for them as well in the Chemistry Reviews, as well as other articles within the Chemistry International, that is the news magazine of IUPAC. So we have also supporting, of course, and celebrating the Global Women Breakfast. And we have here 2 pictures from 2020 and 2021 in which we have been celebrating. We have been celebrating a lot in Portugal. We have more than 15, I guess, organizations and institutions that celebrate and propose themselves to organize. So we'll be having as well a new Global Women's Breakfast next year, February 16. So please go to the website, and of course, we'll be very happy to have, again, the same institution as well as many more joining us and bringing Portugal to light as well within the IUPAC. So another project is the experiment competition that we are running within the IOICN, that we want really to showcase in the simple way, so how we can disseminate chemistry among the community. So the idea is that to show experiments that can be pursued by anyone without any background or very specific background knowledge and without any specific equipment or materials. And here you can see the different competitions that we have been organizing. So all of them devoted to also to the SDGs of the United Nations. And this year the competition is on the food chemistry. And I know that we have really a huge community. We have seen also in this meeting, in this conference. So please make sure that you are aware of this competition. The deadline is on the 5th of June. So you have 15 days. You have to obey to a series of rules. So you have a template that you have to follow. And of course, you have to describe what are the concepts, what is the background behind the experiment, but anything that you might think regarding the food chemistry, so food, nutrition, agriculture. So this is perfectly covered. And please check this opportunity, and we'll be very happy to receive the competitions by yourself. We have a prize, a cash prize of 250 euros for the winners. And then, of course, the experiment has to be described in English, but then don't worry about the English itself too much, because then if your experiment will be selected, will be the awardee, so we'll be also translating in different languages to increase the reach and to make it available to other younger chemists. So also just to highlight some brief more initiatives. So we are really key to promote the Sustainable Development Goals. This is really key to achieve the 17 goals in 2030. And we are really near. It seems that we are 9 years far, but it passed quite fast, as you know. So we are also engaging and promoting different initiatives in social media. So if you are working in any of the SDGs, and you want to write a news about any specific topic, please get in touch with us. We'll be very happy to put your news in our newsletter that we release during the year, as well as on social media contacts. So please just contact us through this email address that you see in here. Also, just to highlight some other initiatives that we'll be organizing at IUPAC 2021. As I mentioned before, it will be a fully virtual event, but this will really tackle the SDGs. What has been the progress so far? What has been achieved? What are the major challenges? What can we do to pursue the goals to reach to the 2030 goals that we have settled? And we have really very nice invited speakers, so associated with very nice and recognized institutions. So International Year of Basic Science for Sustainable Development, the Strategic Approach to International Chemical Management, and the Global Young Academy. And we have also other talks by other younger chemists that will be sharing what they are doing as individuals or within organizations to pursue the SDGs. We are also partnering with the Younger Chemists Committee of ACS in organizing a soft skills workshop into IUPAC 2021. And this will be mainly highlighting the different initiatives that we have been aiming to promote the soft skills among the network. So I am just finalizing. So I hope that we could get a glimpse of what we are doing and what are our capabilities. Of course, we have adapted a lot due to the pandemic. We have turned much more virtually, but it also is nice to get and to increase the reach and to also to empower to empower young chemists at a global level. Of course, before finalizing, I'd like to thank our sponsors for all the awards, all the initiatives, all the sponsorship to pursue different initiatives. And of course, to all of you for listening to this talk. And again, if you want to get in touch with us, so we'll be very happy to hear from you. You have here our email, our social media contacts, so we are very active. And as well, please, you can also see more information at our website. And with this, I finish, and I'm very happy to answer any question that you might have. Thank you very much.
Thank you very much, João, for that thorough presentation. I don't think there are any questions from our audience. So probably we are a little bit over schedule. So I would like to thank you very much. Your information is on the screen, so for everyone who wants to contact. And now, without further ado, we will go on to the Portuguese Young Chemist Award, which is attributed by the Young Chemists Group of the Portuguese Chemical Society. It is focused on scientific impact and awarded every second year to a recent doctor, who is under 35 years of age. So it was awarded last year to João Medeiros Silva, who works at the Utrecht University in the Netherlands. So it was awarded last year to João Medeiros, and he is now going to present the work that was awarded. So it's my pleasure to introduce João Medeiros. The stream is yours.
Thank you very much. Can you hear me? Can you hear me? No?
Yes, perfectly.
Okay.
Perfect.
Okay, I think I'm sharing my screen now. Thank you very much for for the kind introduction. I wanted to thank the young chemist Portuguese group from the Portuguese Chemical Society for this award. I also wanted to thank the organization of this meeting, and also thank our sponsors, the Portuguese Chemical Society, Molecules, and Gravida for this prize. It's really, to me, it's really a great honor to receive this distinction. And given the nature of this talk, I would like to start with the acknowledgements. So this is Marcus Weingart. It's my PhD supervisor. I am really grateful for all the supervision that he gave me and all the orientation. And you can check his website, please do. I also wanted to thank all my colleagues and my master students for all the input and support. This is Eycm Podcast, our key collaborator on the lipids work part. Really grateful to him as well. I also wanted to thank our Utrecht Nmr group for the daily support. Now I'm going to present you a fraction of my work, which is called high resolution solid state NMR of antibiotics that were measured directly in the native cellular membranes of bacteria. And by doing this, we can capture exactly what is the real structure of these antibiotics and how exactly do they work. This was performed at the Bijvoet Institute at Utrecht University. I'm not working there anymore for already 6 months. I'm already into my postdoc here at the MIT. And I would like to start by explaining why antibiotics are important. I feel that I don't need to explain exactly why antibiotics are so important for modern medicine as we know it. Without it, we couldn't have surgeries, for example. So it's extremely important to have highly functional and efficient antibiotics. But the problem here is that bacteria develop resistance to our available antibiotics at a much faster pace than we can replace with new ones. And over time, this leads to a shortage. It's predicted by the WHO predicts by 2050, the number of deaths related to antimicrobial related resistant infections can surpass those of cancer today. And these effects are going to be exacerbated by the COVID pandemic nowadays, because doctors are much more prone to prescribe antibiotics to patients that are not confirmed to have bacterial infections. They're out of precaution because the healthcare is overwhelmed. So we really have to come up with better, more robust antibiotics that are less prone to microbial resistance development from bacteria. And we have to do it very soon. One particular mechanism that we can exploit to produce new antibiotics are those antibiotics that interfere with the cell wall with the cell wall formation of bacteria. So as you know, bacteria has a cell wall that is extremely important for its survival. And this cell wall is composed by peptidoglycan. And the bacteria have to be constantly replenishing this peptidoglycan layer. And it does so through a cycle called the lipid 2 cycle. Now, lipid 2, it's composed by a pyrophosphate motif, an isoprene lipid shell, and a peptidoglycan subunit, a MURNAC and a GLUCNAC. And lipid 2 transports these peptidoglycan subunits from the inside of the cell to the outside of the cell, where the bacteria will form the peptidoglycan layer. Now, it happens that certain antibiotics, such as the former last resort antibiotic vancomycin, it binds to this peptide unit. And by doing so, it sequesters lipid 2 and blocks away this lipid 2 cycle, and the bacteria dies. But the problem here is that antibiotics that bind to these pentapeptide motifs of lipid 2, and peptides being peptides, they are prone to mutations. So the bacteria can very easily develop resistance against these antibiotics. Other antibiotics, peptide antibiotics actually, they rather bind to this pyrophosphate motif of lipid 2. And this is very interesting because if you think about it, the bacteria cannot simply mutate away a pyrophosphate group form of phospholipid. So antibiotics that act in this mechanism are much less prone to the resistance development by bacteria. Such examples is, for example, the antibiotic Texobactin. It binds to this lipid 2 and blocks the lipid 2 cycle, and bacteria readily dies. It forms these large clusters in the membranes. Other antibiotics, such as niacin, actually does more than this. When it binds to lipid 2, it also forms spores, and these spores punctures holes in the membranes of bacteria, and the bacteria bursts and collapses, and the bacteria more efficiently dies. So what is my goal here? I want to understand what are the molecular features of these antibiotics that are responsible for the binding of this pyrophosphate motif, because if we know the molecular basis for this binding, then we can use this knowledge for future drug design studies of new antibiotics. Also, I want to study this directly in the membranes of bacteria because I want to understand what are the biophysical mechanisms that bacteria develop that lead to resistance development against these antibiotics. So I'm going to present you our arsenal. So this is our bullets. So this is Nisin. It's a peptide antibiotic. It's composed of 34 residues. This antibiotic is produced by milk bacteria. And I figured out a way to label this antibiotic with nitrogen 15 and carbon 13. Look that this antibiotic has non-common amino acids such as dehydrobutyrene, dehydroalanine, and these lanthanine rings. Notice that these are not disulfide bridges, these are thioether bonds. And this peptide binds to the lipid 2. And now we want to understand exactly how. The other antibiotic is called Texobactin, was discovered recently in 2015 in a soil bacteria. Now this antibiotic is a little bit more, it also has some weird features. It has this Pepsi cycle, that is a cycle here at the end of the peptide. And it's also composed by DEL amino acids. Now I did not label this peptide myself, our collaborators did this. And they managed to label only DEL amino acids of the Texobactin. The D amino acids was way too expensive to obtain. Now, to label our target, in order to study it by NMR, we have to label lipid 2 as well. And the lipid 2 total synthesis was already described recently as well. But if we want to label, this route becomes prohibitively expensive. So I figured out a way to label the precursors, the building blocks of lipid 2, UDP glucnac and UDP murnac pentapeptide in bacteria by Staphylococcus simulans. And then I also extracted the pyrophosphate isoprenyl chain extracted from bay leaves. And then I administered these components to fresh bacterial membranes of bacteria that have the enzymes still working. The enzymes are still intact. So I mix everything, and after a few hours, I can produce milligram quantities of this labeled lipid 2 that I can then extract from the membranes and then purify and then proceed to our NMR studies. So to study this system by NMR, I have to apply solid state NMR. So I introduce lipid 2 inside the liposomes, and then I mix our antibiotics with the liposomes, fill in our NMR rotors, and then proceed to acquire the spectra. So just to show you the difference between solution state and solid state NMR, here are you seeing a HSQC of Nisin that bound to lipid 2 that was measured in the MSO. So because it's the MSO, then you don't have a bilayer. And since you don't have a bilayer, you don't have the pore conformation. This means that, and when we went to solid state NMR, now you are studying the whole system in bilayers. And now, as you can see, the spectrum is completely different. That means that the structure that was calculated before is actually not biologically accurate. And now we are in the right conditions to fully describe the system in its relevant conformation. We managed to obtain nitrogen, proton, and carbon chemical shifts that fully describe the Nisin lipid 2 system. We managed to identify all the signals by using 3-dimensional NMR. And then to get the structure of the Nisin inside the pore conformation, we use this carbon spectra. These carbon spectra, these are spin diffusion carbon spectra, and they work just like NOESY spectra in protons, in the sense that we can obtain long distance restraints that occur through space. We can identify which nucleus are close to each other, and then we can use these restraints, I obtained over 300, to calculate the structure of our antibiotic Nisin. It forms this spiral-like shape that is, as you can see, it's completely different from the structure that was obtained in the MSO. Now, to identify the binding motif, I resort to phosphorus NMR. So lipid 2 has 2 phosphorus groups, right? And we can also do NMR in these phosphorus. So here we are seeing the 2 phosphorus signals, and then I can correlate back via HSQC-like spectrum which protons from the peptide are in close proximity with these phosphorus groups, which corresponds to the first groups of this peptide. So I can use this information as distance restraints to dock our peptide into lipid 2. Next, by using the labeled lipid 2, I managed also again to do this carbon spectra to get the confirmation the head group of lipid 2 and get the whole structure. So here, as you can see, we see transfer of carbon magnetization between our peptide and only the first sugar, the murnak of lipid 2, but we don't see any contacts with the glucnak of lipid 2. That means that only the first sugar is important for binding. The second sugar, the glucnak, it's actually not important for binding to lipid 2. Now we got the structure of lipid 2 docked to our peptide. All that is left is to define the dimerization interface. And to define the dimerization interface, I labeled half our pores with nitrogen and the other half with carbons. And then I transferred the magnetization from nitrogen to carbon. And that way I can define only the signals that are occurring at the interface, which I can use again as distance restraints to calculate the entire structure of our dimeric units. So right now we are in the stage that we are assembling all these units into a pore to get the full pore structure. Now for Texobactin, we're gonna repeat the same type of work. This is the NH spectrum of Texobactin in liposomes, and here in gray you see in free in solution state without lipid 2. So you can see that this is indeed the bound state. And we also obtained the carbon spectrum. Judging from the carbon chemical shifts, we can see that the first segment of Texobactin actually forms a beta sheet. And to get the structure of this beta sheet, we resort again to these carbon-carbon spin diffusion experiments to get long restraints, distance contacts. And we see that we have contacts between the first isoleucine towards the last part of the peptide. And this distance is way too long. It's over 15 angstroms, which is way too long for the magnetization transfer to occur from this part to this part. But it's possible if these beta sheets are actually forming anti-parallel beta strands that oligomerizes in the membrane. Now to get the structure of our docking structure of our lipid 2, we again do these phosphorus measurements. And then we again can identify where is it binding. It actually binds towards this ring, this weird ring motif of Texobactin that is conserved, this Depsy cycle that is very important for the binding to lipid 2. And that's how we can manage to dock our structure. Then we assemble all our information and calculate the full structure of Texobactin that actually forms a beta strand clustering on top of the membrane, which then explains why we see these clusters formation here in the lipid membranes. So all the studies that I showed you thus far were performed in pure reconstituted liposomes. But as you know, bacteria are much more complex than that. And bacteria, membranes of bacteria can have the real native cellular environment can have crowding effects, pH variations, and other proteins that can impact how the antibiotic binds to bacteria. Also, the receptor lipid 2, it varies across bacteria. And indeed, we know that one antibiotic can have very different responses towards different bacteria. So we want to understand exactly what are the features, the biophysical features of the membranes of bacteria that are responsible to modulate the efficiency of this antibiotic. And in order to do this means that we have to do these studies directly in the native membranes of bacteria that were not possible before, but thanks to the advancements that I did in the beginning of my PhD, it's now possible to do it directly in the cellular membranes, in this case of Micrococcus flavus, which is represented here by the pink spectra. As you can see here, we see in blue the regular spectrum in liposomes that correlates very well to the same state that happens also in the real bacterial membranes, with a few exceptions that corresponds here to residues 21 and 22. We went to measure the carbon spectrum. Again, the same thing happened. This was measured with dynamic nuclear polarization, by the way. And we see again the same variations that corresponds to residues 21, 23, and 13. So we consistently see that there are some differences regarding these linker regions of the peptide.
Wrap it up. We are very short on time.
Just one more slide. Just one more slide. So we want to understand exactly how this variation happens. We want to measure the same spectrum. We realize that these Micrococcus flavus have very thin membranes. So when we measure in different membranes, we see that these linker domains, they vary according to the thickness of the membrane. And indeed, we saw that these linker regions, they have the flexibility necessary to adapt to the thickness of this membrane. So what does it mean for the antibiotic itself? It means that the antibiotic evolved these linker domains to adapt the antibiotic structure towards the local properties of the bacteria. And this makes total sense because if you think about it, the antibiotic has to work against different bacteria that have completely different membranes. And this was also corroborated by biochemical studies where they saw when they truncate away these segments, then the antibiotic only works against bacteria that have very thin membranes. It does not work against bacteria that have very thick membranes. So we are seeing here a clear correlation between antibiotic cellular adaptability and the efficiency of this antibiotic. And I'd like to just to go to the conclusion. So here I developed methods to determine the structure of lipid tube binding antibiotics directly in their physiological settings. I managed to develop methods for the labeling of antibiotics via biosynthesis and labeling of the target lipid targets via biocatalysis. And this is the method with solid state NMR to study the pharmaceutical relevant state of these antibiotics. I'm very sorry for being a little bit overdue. And I would like to thank again my group, our collaborators, and also the funding and you for your attention.
Thank you so much, João Medeiros. It was an insightful presentation, and I'm clear that it was well deserved, the PYCHE award. So thank you very much, and congratulations on winning this award. It was a very nice presentation. So without further ado, let's go and see now who won the Retrosynthesis Award. So I will ask João to stop sharing his screen so I can pass the streaming to Dr. Paulo Vital, who will continue with this section.
Boas tardes a todos. A Márcio, sou eu que tomo conta do processo, Artur Silva, e por isso gostaria de saber se o Paulo já está cá, já está.
Já estou cá. Olá, professor, boa tarde.
Tudo bom?
Tudo bem,
e
obrigado.
Por isso espero que já estejam também cá os envolvidos para saber que eles são premiados ou não, e por isso eu aproveitava este momento para agradecer à Bial, na pessoa do Paulo Vital, toda a colaboração que prestaram mais uma vez, à organização do PYCHeM, em particular à Sociedade Portuguesa de Química, neste processo. É sempre com prazer que temos a Bial, e a Bial tem sido um bom companheiro nestes processos de congressos da divisão de Química Orgânica e da Química Terapêutica. Como eu já disse há bocadinho na sessão, foi uma iniciativa muito animada, que foi a Paula Branco e foi a Emília de Souza, por isso as senhoras presidentes das divisões de Química Terapêutica e Química Orgânica que puseram este desafio, que correu bem, teve 9 equipas envolvidas, com muito trabalho. Depois o júri teve alguma dificuldade a escolher as 4 finais, e há bocado nas 4 finais também tivemos umas apresentações bastante interessantes, tivemos jovens a estarem interessados nesta área, que é sempre um pouco difícil, e por isso dar os parabéns a todos os envolvidos, às promotoras, e também aqui ao PYCHeM, porque acomodou rapidamente este desafio, em particular à Inês, que acomodaram este desafio e fizeram integrar parte deste processo. Mas antes de dizer quem ganhou, porque senão depois já ninguém o ouve, eu vou dar a palavra ao Paulo Vital para falar um pouco sobre o processo, porque senão depois, se eu der o nome, já eles calam-se logo, por isso eu vou só dar assim a palavra e depois nós damos quem é sim.
Ok, muito obrigado. Então é assim, boa tarde a todos. Eu gostaria de agradecer a oportunidade e o convite de estar aqui hoje, portanto, em representação da Bial. Eu sou um membro relativamente novo em Bial, portanto, este tipo de organização e de eventos também é novo para mim, mas é bom saber que de facto que nós temos aqui uma pujança em termos de química orgânica particularmente em Portugal. Portanto, gostaria de agradecer a oportunidade de aqui estar hoje. Gostaria também de dar os parabéns a todos os participantes, porque foi dito que houveram 9 candidaturas e que se escolheram 4 finalistas, mas muito obrigado a todos os que participaram. Muitas vezes, quando se faz uma avaliação de propostas, tende-se a ser muito pragmática em função daquilo que tem maior probabilidade de funcionar, mas às vezes aquelas ideias mais radicais são aquelas que acabam por, de facto, abrir avenidas de investigação que não são antecipadas. Portanto, isto é um bocadinho para motivar aqueles finalistas ou aqueles participantes que não chegaram à final. Eu vi as 4 apresentações, apesar de estar com a câmara desligada, portanto, parabéns, foi no geral bastante bom, houve um cuidado de tentar motivar as transformações propostas nas vossas propostas em função daquilo que havia precedentes, portanto bom. Houve um cuidado de tentar antecipar aqueles passos que seriam mais problemáticos e tentar propor soluções, bastante bom. Houve um sucesso relativo, mas ainda assim um sucesso na resposta às perguntas colocadas, portanto no geral achei bastante bom. Gostaria de agradecer em particular à organização. Isto é uma área que para mim em especial é muito querida, porque é a minha core expertise, essencialmente síntese de produtos naturais, e como foi dito, é uma área que não é fácil. É uma área que é ingrata porque, comparativamente a outras áreas, em termos de publicações, geralmente fica sempre aquém. Hoje em dia é cada vez mais difícil conseguir financiamento baseado numa proposta de síntese. No entanto, eu posso dizer isto, se calhar, um bocadinho para motivar quem está na audiência, que praticamente todos os meus colegas que trabalham comigo no Laboratório de Investigação Química em Bial têm um background em síntese orgânica. Poderá ser alinhado com, por exemplo, o uso da chiral pool, como algumas das propostas tiveram, poderá ser dentro de um desenvolvimento de metodologia que depois é aplicada num passo particular de síntese, mas de facto é um treino bastante importante. É fundamental na indústria farmacêutica e, portanto, este tipo de iniciativa que fortalece e que divulga a síntese orgânica é extremamente importante para que, esperemos, no futuro hajam mais biais por este Portugal fora. Portanto, muito obrigado e da parte que me toca, a nível pessoal, eu espero que seja o primeiro de muitos destes eventos. Obrigado, boa tarde.
Obrigado, Paulo. Pois é que este senhor que também está a falar, para além de Presidente da Sociedade de Química, também é químico orgânico. E por isso percebo perfeitamente estas questões. Bom, já agora gostava que os candidatos que estão aqui sem cara, ainda que ativassem os que participaram todos, exatamente, para também serem conhecidos dos outros que são as pessoas, os colegas que estiveram envolvidos neste concurso. E por isso há aqui câmaras interessantes que têm os 3 participantes no mesmo sítio, outros que estão, os outros estão um bocadinho espalhados por este processo todo. Bom, eu agora já não vou dar mais seca, não é? E por isso existiu realmente foi difícil nós escolhermos, só escolhemos um, não há mais menções, nem coisa que se pareça, acho que os outros estão em igualdade de circunstâncias. E por isso, o vencedor da primeira competição nacional de Retrosynthesis 2020, como tem ali a Paula atrás da cabeça dela, foi o grupo de M&M's. Por isso é o Diogo, a Ana Sofia e o Nuno que estão ali, e por isso esses foram os que foram os premiados desta primeira competição. Os meus parabéns.
Obrigada.
Obrigado. Muito obrigado.
Parabéns.
Parabéns.
Obrigado.
E bom, agora devolvo ao Márcio, devolvo a si ou devolvo à Inês a situação?
Pode ser a mim, professor Artur, muito obrigado. Muitos parabéns ao grupo M&M's e a todos os outros grupos que participaram nesta competição. Como estamos muito apertados de tempo, vou então mais uma vez felicitar todos e agradecer terem participado. E vamos então agora, we are going now to continue with our schedule. So the award of the Retrosynthesis award was handed to the M&M's group, and now because we are a bit short on time, we are going to deliver the best oral award, which is given by Ready to Pub. So I will send the word to Ricardo Malheiro. The streaming is yours, please.
Thank you, Marcio. Good afternoon, everybody. Can you hear me?
Yes, perfectly.
Okay, thank you. Good afternoon. My name is Ricardo Malheiro. It's a pleasure to deliver provide this award in the 7th PYCHeM. At this moment, I'll try to be as quick as possible. I understand that the time is short, so I'm sharing now the Ready to Pub award. So the Ready to Pub award will be awarded to José Paulo Lopes Roque from the University of Chemistry, with the communication age tunneling activated upon vibrational excitation. So congratulations, José Paulo Lopes Roque. The Ready to Pub award is English editing service, completely free. So then you will receive instructions on how to reclaim this award, okay? José Paulo Lopes Roque, congratulations. Now, the second award that I'll announce is the Best Oral Communication Award. This award is not provided by Ready to Pub, okay? It's Solitica. It's a company of material and reagents as well. So Solitica, the Best Oral Communication Award will be provided to Fernanda do Carmo Machado Silva from the University of Aveiro, with the communication influence of processing parameters on coffee compounds hypocholesterolomic potential. So congratulations to all the winners, and thank you for this partnership and for the opportunity to include Ready to Pub as one of the partners of this organization. Okay, thank you very much.
Thank you, Ricardo. So we are now going to deliver the poster award, the best poster award. From me, it's all, so I will send the streaming over to you, Inês. Thank you.
Hello, everyone. Thank you for the exciting lectures that we have seen this afternoon. This will be very, very quick. So the best poster award is given to, this is not 1, 2, or 3. So yeah, there are 3 best poster awards. So let me see. So the 3 best poster awards will be given to André Luz with the title Entitled Synthesis and Study of a Novel Class of Potent Necropsis Inhibitors. The second will be to Ana Cláudia Negrão for the poster Hypervalent Iodine Reagents Exploring the Potential of Unpulling Reactions, and also to Andrea Silva with the poster entitled Applications of Resveratrol Delivery Systems for Functional Breath. So congratulations to all the awardees, and let's move on. Thank you, Marcio. I don't know if Marcio is here or not. So yes, I think, yeah, I think we can close up this session and move on to the closing ceremony. But if you want to say a few words or something.
No, just to say thank you very much. It was a pleasure to be here, and we can continue. Thank you very much, Inês.
Thank you so much. So let's move to the end of PYCHeM. This is the beginning now of the closing ceremony, and we have the pleasure to receive here the Secretary of State, Dr. Isabel Ferreira, that I will give now the word. Thank you, Professor Isabel, and welcome to our Congress.
Thank you very much, Inês. And first of all, I would like to endorse my compliments first of all, to the organizing committee, these young chemists. And I would like to name all of them: Carla Pereira, José Pinella, Maria Inês Dias, Ângela Fernandes, Sandrina Heleno, Márcio Carocho, Cristina Caleja, Eliana Pereira, Filipa Reis, Bruno Melgar e Oludemi Tofik. And I would also like to endorse my compliments to the president of the Polytechnic Institute of Bragança that hosts this Congress, and also the director of the Montaigne Research Center, and Professor Artur Silva as president of the Portuguese Society of Chemistry. And it is a real pleasure to be with you. And since it has been established in 2008, the Portuguese Young Chemists Biennial Conference is progressively recognized as privileged forum to gather young researchers from all chemistry subfields and other related scientific research areas. And the current 7th PYCHeM meeting is an example and reinforces the potential of this event to attract young chemists and researchers from different nationalities, allowing them to share scientific achievements among their peers and expand international research networks and attend lectures from reference chemistry experts. In this edition, the opportunity to learn the latest developments in several chemistry fields is emphasized by the quality of the scientific program, which includes 2 plenary lectures, 10 invited communications, and 32 oral communications. And furthermore, the participants will have the opportunity to evaluate a high number of poster communications. And as we all know, scientific activity might reach excellence in any part of the globe. Accordingly, the location of any scientific event should not be considered as a primary factor. Nevertheless, I must highlight the fact of organizing such a prestigious event in a city that is classified as a territory of the interior. These networking dynamics involving higher education institutions, industrial companies, associations of local development, and other local agents such as municipalities or intermunicipal communities is the main basis supporting the activities developed under the program for the valorization of the interior. And this program aims to promote an evolutive increase in the competitiveness of territories and employment creation, anchored in medium-sized cities and, of course, their areas of influence. So our program is operationalized in 4 fundamental axes: valuing endogenous resources and business capacity in the interior, promoting cross-border cooperation for the internationalization of goods and services, capturing investment and fixating people in the interior, and making the interior territories more competitive. And the proposals associated to each of the previous axes are materialized as differentiated measures, able to achieve an interoperability of greater proximity, without any doubt, scientific innovation and technology hold a relevant position in our program, and we have been supporting science in great extent, as evidenced, for instance, by the investment in high qualified human resources in companies and also in entities of the scientific and technological system, but also by supporting for the attraction of young people to the interior, or even the funding of collaborative laboratories. And we also support investment in innovation, whether in terms of research and technological development or production, stimulating partnerships between companies and academia and national production. So this progressive commitment with innovation strategies is only possible by guaranteeing adequate knowledge levels and by fulfilling the premise that research and innovation must be a priority of all regions, with very positive contributions to make all territories economically competitive in the global context. However, these political initiatives are just the starting point. The scientific community must be aware of all funding opportunities, not only national-wide, but also at the international level. And it is mandatory to define the adequate strategies to achieve the best possible use of different financing axes to guarantee a more efficient mobilization of funds in interregional, national, and international cooperation programs, but also to conduct coordination actions to acquire funds that acknowledge competitive excellence or achieve higher levels of critical mass based on the complementarities of training and knowledge existing in different territories. These objectives represent some of the challenging tasks that all research groups should be dedicated to, and the targets are identified. Now it is necessary to dedicate the best efforts to achieve their completion. So finally, I endorse once again my congratulations and acknowledgement to the organization, and I am very proud of all of you. Thank you very much.
Thank you so much, Professor Isabel. It's an honor for us, you know. It's an honor for us to have you here with us in this moment. We have been planning this event for a very long time, and it's time to move on, for, as they say. And it's an honor also to hear you say those words. For us, it's very important. Very important. It's I don't know. It's really proud to have you here. We are very proud to have you here, and to hear you say that. And well, thank you so much for being here with us in this day. Thank you so much, Professor. If you want, you can stay with us and to the final session. But we know that you have a very full agenda, and we see you around. Thank you so much, Professor.
Thank you.
Thank you so much. Bye. See you. See you soon. Bye. So let's finalize, or let's move on to one of the final steps of this closing ceremony. As normally, as tradition, in the PYCHeM closing ceremony, we present the next PYCHeM event where it's going to be held, and it's going to be in Villarreal by our colleagues from the chemistry department of the University of Trás-os-Montes e Alto Douro, from UTAD. So we have here with us, I think it's Mariana Fernandes that is going to,
yes, correct,
to have a very small presentation about the venue and about the event. So Mariana, the floor is yours. Thank you so much.
Thank you, Inês. It's a great pleasure to receive your invitation. I hope to be, I'm very honored by your invitation. Can I share my screen? Can you see?
Yes, Mariana. It's
okay. So I will start. Thank you. Welcome. Good afternoon, everybody. Since 2008, PYCHeM is traveling around the country. For the reasons that we all know, this week the conference was virtual and it was excellent, but it was not possible to visit the beautiful city of Bragança, maybe in a next time. But I'm here today to invite everyone for the next PYCHemistry conference, the 8th meeting, that will be hosted at Villarreal in 2023. Villarreal is located nearby the Douro Valley and surrounded by the beautiful mountains of Alvão and Marão. The city has a well-known history which can be appreciated in its sites, monuments, and people. For instance, you can visit Palácio de Mateus, Museu da Vila Velha, or the theater. The university stands one of the main pillars of regional development, providing an advanced set of skills to all who turn to it. More recently, Régio Douro Park is also an important factor in the development of the city. Vila Real is also known for the gastronomy, with conventual sweets such as Crista de Galos or the traditional pies called covilhas. The city, one of the most popular events that occurs in June with the WTCA race. You should visit the city during this time to understand it. It's impossible to describe and to understand the magic that happens during these days. Let me show a small video presenting our university. It's very small. Our research is based, as you said, Inês, on the Centro de Química of Vila Real. We have 4 main research areas: environmental chemistry, food chemistry and biochemistry, materials chemistry, and applied organic chemistry. The city is not far away from the rest of the country. As you can see, the distance from Lisboa, Porto, Bragança, it's not so big as usually the people knows. And the accommodation is also not so expensive. So at this point, I hope I convinced everyone to come to Vila Real, and I hope to see you soon. Thank you so much.
Thank you so much, Mariana. We are very looking forward to the next PYCHeM, to the 8th PYCHeM 2023. Hope everything goes well. Hope it can be presential. Hope you can see and have the opportunity to visit your city and your university. So thank you so much for your presentation. And good luck for the next organizing committee. And you still have 2 years, but a lot of work in front of you. 2 years, yes, 2 years, and a lot of work in front of you. So good luck for you and congratulations.
Thank you.
Thank you so much.
Thank you. Bye.
So we are finalizing the PYCHeM. Just very few words, like final notes of the Congress. Just for you to know, the overall participants are, we had 255 inscriptions, 199 submissions of work, 2 plenary lectures, 10 invited lectures, plus the 2 lectures from the European Young Chemists networking, and also the PYCHA winning lecture. Also, we had 32 oral communications plus 4 oral communications from the National Retrosynthesis Award. It is really a joy for us to present these numbers, not only for the quantity, of course, but also for the quality of everyone involved. All of them in the different areas of the chemistry they are working are of an excellent scientific quality. We sincerely hope that this was a very fruitful event and that everyone was able to learn and take advantages of this shared science. So I would like, on behalf of the organizing committee, to thank all the members of the scientific committee who, with the evaluation that they provided of the submitted work and with the moderation of the sessions, made and validated the excellent quality of the Congress. Thank you to the plenary and the invited speakers for the availability to be here with us and to share with us your excellent work and the future perspectives that we can have in the different fields of chemistry. Thank you also to the younger speakers that have been here with us to present the oral communications, but also the poster communications. Also to the Honorable Secretary of State for gracing us with your presence here with us in this closing session. Thank you to the President of IPB and the President of SPK, Professor Artur Silva, for the words of encouragement in the opening session, but especially for the President, Professor Artur Silva, for all your availability and all your help throughout this process of organizing the Congress. To the Ready2Pub company for the availability of providing the webinar in the day before the Congress and for sponsoring the dissemination of the 7th PYCHeM through all your networks and through all your chains of communication. To all the sponsors of the Congress, also to Molecules Journal for sponsoring the PYCHA Award, to Leonardo Mendes and Cristina Campos for all the support, help, and availability during this year and a half that we have been organizing the Congress. Finally, to all of you for your participation, and if not before, we see you at the PYCHeM 2020 in Villarreal. Thank you so much. If anyone has a comment to say, if anyone wants to talk about, please share with us your comments and wishes. And I don't know if someone else wants to give a word. I don't know. So in the YouTube section, there's nothing else. I don't know, Professor Artur, do you want to share something with us, please?
Yes, I can share one thing. Congratulations to all of you for the excellent work that you have done.
Thank you so much, Professor. Thank you for all your help, and we see you around. Hope to work with you in another time and in another place. So thank you so much.
Thank you.
Thank you. So without anything more else to say, we say goodbye and see you around, all of you. Thank you for participating.